All right, looks like we're live again. Just to jump back into things, I'm now finishing up the lectures of the class. So I did kind of all the work of the project in two sort of chunks where I try to do the first 10 lectures and the first 5 problem sets, of which I finished the 10 lectures and I've done most of the problem sets. There's still a few questions that I either didn't do because I didn't have the software installed or because I wanted to brush up on some things first. And what I'm going to do now is working through the rest of the 14 lectures. So I think we were on lecture number, let me just double check here. Yeah, lecture number 13. So there's 24 lectures. So for the next couple days, I'm going to be just finishing up these lectures. The reason for doing all the lectures at once rather than doing them with the problem sets, with the practice in the kind of sequence provided by MIT, is just simply that there's a little bit of a trade-off point. The trade-off is that if you do them sequentially, you will have practice in between, so you are better able to understand the things that happen in later lectures. So you don't get in this situation where you don't really understand something, it's just getting more and more bewildering as you move on. The other flip side of that, though, is that if you do it in that process, then you also get into this situation where you may do a lot of practice on stuff that you kind of understand fairly well, and you don't have enough time to practice stuff that you are struggling with. Now, because this is a limited time project period, I'm devoting a month to this. I have sort of set studying hours. I am trying to do this sort of the way that I would do a class in the MIT Challenge. In comparison, the MIT Challenge, I'm studying a bit less, but at the same time, this class is also, I would say it's not, I don't want to say for sure that this is like definitely harder than all the classes that I took in the MIT Challenge, but it's definitely in the harder end of them. There were a lot of classes that I found a lot easier than this one. And I think it's just because I found classes in the physics, calculus direction harder generally. I struggled a lot more with, let's say, 1803 differential equations or 802 electromagnetism. I struggle with those more than, a lot of the computer science ones. And that just might be my background. It might just be an intrinsic difficulty of those classes. And this one's 804 and I'm missing one of the prereqs. So it's definitely on the harder end, which is also why I'm taking a little bit longer to do this. I'm not trying to do it in a week or something like that. And so basically I've been kind of balancing that trade-off point, deciding to cut it into 2 chunks. I may cut it into 3 chunks if it starts to feel like, okay, I need to take a break and practice and work on some of these concepts before I come back and do more lectures because it's going over my head. But at the same time, I do feel like when you're watching the lectures, basically watching the lectures and following the lectures is a considerably easier task than doing the problem sets. So even if you are not nearly at a point where you have learned the material, you can still follow the lectures. And that's sort of what I found doing a lot of the MIT classes, is that I could follow lectures one all to the end and follow what was happening, understand what was happening, and then the work would begin where I'd have to work on the problem sets. So that's kind of what we've been seeing here, except just the difficulty level has just been higher because I'm missing some material, and the material that I do remember is fairly rusty. So basically, we started the lectures 11 on yesterday afternoon, and now we are going over to just finish them. So I think let me just check here. We were midway, 44 minutes into lecture 13, which is about scattering. I think this is scattering off of the finite step. Yes, scattering off the finite step. So I'm just going to keep working on this, keep pushing through. My hope is that I can get done. Get done enough so that I'm basically the rate that it looks like I've been doing it is about 2.5 per session, which is not bad. I mean, it's a little slower. I think that's 2.5 per session. They're about an hour and a half each. I thought they were an hour and 15 minutes, but most of them are actually around an hour, 20, hour and a half. So that's, maybe 2.5 would be what, 4.5 hours that I'm doing in 3 hours. Yeah, I mean, it's about 1.5 times the speed. That's a pretty good rate. I don't think I can go much faster than that. And there is the possibility I might have to redo a class. It's hard to know when you're doing a class whether you're going to need to do that or not, because I sort of redid, I don't want to say redid, but I went back through lectures 8 and 9 just because they involved kind of a tricky, long-winded calculation, and one that was the brute force method for solving the partial differential equations for the time evolution of the simple harmonic oscillator, and the other one was the raising and lowering method. And it was just, it's a lot of complicated stuff happening, and they're kind of presenting it quickly, and it's not clear what's motivating each step in the sequence of like, well, why are you deciding to do that? Why are you deciding to do this? So I went through and did them a little bit more closely. I feel pretty good about these lectures now, but if we get into that situation, I'm going to try to catch it ahead of time and stop and slow down and try to brush up. But it's very easy also to be in kind of lecture mode where you're watching and you are writing things down and you're jotting things down, but you're not having that same feedback on your understanding. So it is going to be something that maybe when I start doing the problem sets, I'm going to realize, whoa, actually, maybe I need to go back and work on those. So let's go back and finish this lecture. I'm going to just, let me just quickly set up the screen here. I have to do this each time I set it up. So we'll set up the lecture. As I've said throughout this process, but in case you're just joining me now for the first time, all of these materials are on MIT's website. So if you do a Google search for MIT OpenCourseWare, 2013 spring, and the class is 8.04. And if you find that, you'll find these lectures, you'll find these problem sets, you'll find basically all the materials I'm using aside from some of the textbooks. And we're mostly been using the free online materials, just a little bit on the textbooks. And these aren't even the textbooks that they recommend. So I've just been using them. Just because there's some copyright issues with watching some videos and doing some things that are not through MIT. So I've been kind of leaning on the textbook because it's a little bit easier to get away with. Whereas if I'm streaming a YouTube video that someone has copyright through my channel, I might get the video taken down. And so I have to be a little careful about that. And I don't want to try to hide anything that I'm doing, so to speak. Let me just put my phone on silent here. Always a good step before you start a studying session. All right, so let's jump back into lecture 13.
Looking at your expression for transition probability, yes, I'm having trouble seeing how that works out to 0 when E is less than V naught. Oh, this expression is only defined when E is equal to V naught. Because we derived this, we derived this assuming that we had an energy greater than V naught and the wave function had this form. You cannot use this form of the wave function if the energy is less than V naught. If the energy is less than V naught, you've got to use that form of the wave function. And in this form of the wave function, we derive that the transmission amplitude is 0 because the current on the right, the transmitted current is 0. So this calculation is appropriate when E is less than V naught. This calculation is appropriate when E is greater than V naught. So you're absolutely correct. You can't use this when E is less than V naught because you not the same answer. In fact, it gives you a complex. It's kind of confusing, right? The factors can't, but so it's not really a probability at all. And indeed, this is just not the right quantity to use. Cool. All right. So so there are a bunch of nice things I want to deduce from what we've done so far. So the first is, look, I pointed out that this can be derived just explicitly, and it gives the same results as before. That's not an accident. If you take the system and you just reverse the roles of K1 and K2, what happens? Well, that just replaces E by E minus V naught if you do that by doing this. Replaces E by E minus V naught and E minus V naught by E, it swaps the role of A and B, and it gives you exactly the same things back. So if you're careful about that, you never have to do this calculation. You can just do the appropriate transformation on that calculation. It gives you exactly the same things. It's the same algebraic steps. But the other thing that's nice is that you can actually do the same thing from here. So as long as you set the D equals 0, so there's another term here that we debugged, the plus alpha x, and we got rid of it. But you can analytically continue this calculation. By knowing that, look, if we just set alpha, we have minus alpha equals ik2, then the algebra is all going to be the same. We just have ik2 instead of minus alpha, so we can just replace alpha with minus ik2 everywhere in our expressions, being careful about exactly how we do so, being careful to take care of factors of I and set correctly, and you derive the same results for both cases, which is a nice check on the calculation. So often when you get a little bit of experience with these, you don't actually have to do the calculation again. You can just take what you know from a previous calculation and write down the correct answer. So it's a fun thing to play with, exactly how do you do that. So I invite you to think through that process while you're doing a problem set. Another thing is the reflection downhill thing, which is pretty surprising. But here's the thing that I really want to emphasize. What this calculation shows you is not just that reflection downhill is highly unlikely, or sorry, transmission downhill is highly unlikely when the energy is very close to the height of the potential area. That's true, but it's not the most interesting thing about this calculation. The most interesting thing about this calculation, to my mind, is the fact that from the detailed shape of the transmission as a function of energy, we can deduce what the potential is. And let's think about what that tells you. If you do an experiment, you have a barrier, and you want to know the shape of the barrier. Is it straight? Is it wiggly? Does it have some complicated shape? And how do you measure that? Well, you might measure by just looking. But imagine you can't for some reason. For whatever reason, in a box, or you can't look at it because it's preposterously small. How can you deduce what the shape of that hill is? Well, one way to do it is to send in particles as a function of energy, more and more energy, and measure the probability that they transmit. Okay? Now, if you do so and get this graph as a function of E, what do you deduce? You deduce that the barrier that you're scattering off of is a square step with this height V0. Are you cool then? So apparently, just by looking at the transmission amplitudes, or transmission probabilities, you can deduce at least something of the form of the potential, which is kind of cool. If you didn't know the potential, you could figure out what it was. And this turns out to be a very general statement that you can deduce an enormous amount, and as we'll see, you can in fact deduce basically everything you want of the potential from knowing about the transmission probabilities as well as the phase shift, the transmission amplitudes. Okay, so this is the basic goal of scattering. And so the way I want you to think about it is, imagine, for example, that someone hands you an object, a box, and the box has an input and it has an output. Okay, and they allow you to send in particles as a function of energy and measure transmission and reflection. You measure transmission and reflection, just like I'm measuring transmission off of your faces right now, and from the light from above. So suppose that you do so, put it on your test stand, and you measure transmission. You measure transmission as a function of energy, and you deduce, and you observe, well, the transmission as a function of energy is small up until some point, and then at some point to make the minimum energy you can really meaningfully probe, you get something like this. Okay. So here's the transmission as a function of energy. So what can you say? If this is all the information you have about what's going on inside the box, what can you deduce about the thing inside the box? Well, one thing you can deduce is that it looks kind of like a potential with height around V0. It looks kind of like a potential step with some height V0. This is asymptotic to 1. However, it's not, because it has these oscillations in it. So there's more to the potential than just a barrier of height V0. What I want to show you is that you can deduce everything about that potential. And that's the point of scattering. So let's do it. So the goal here, again, to say it differently, is what's V0? Or what is V0? Not just the height, but the total potential. So another way to say this, let me set up a precise version of this question. I want to be able to do the following. I want to take a system that has potential which is constant up to some point which I'll call 0. And then again from some point which I'll call L. It's constant again. And inside I don't know what potential is. Okay? So in here there's some unknown potential V of X, which is some crazy thing, right? It could be doing anything. It could be some crazy, it could have, horns and whatever. It could be awful. But the potential is constant if you go far enough away. And the potential is constant if you go far enough away. A good example of this is like a hydrogen atom. Right? It's neutral, but there's clearly a complicated potential inside this. The proton and the electron are moving around in some quantum state anyway. And if you send something at it, far away, as if it's not there, but close by, you know there's strong electrostatic forces. And so the question is, what can you learn about those forces? What can you learn about the potential by throwing things in from far away, from either side? Now, one thing we know already is that out here, the wave function always, because it's a constant potential, always takes the form e to the ikx plus b e to the minus ikx. And out here, it takes the form c e to the ikx plus d e to the minus ikx. And again, this corresponds to moving in. D is in from the right. C is out to the right. B is out to the left. And A is in from the left. And so again, there are basically 4 kinds of scattering experiments you can do. You can send things in from the right, which corresponds to setting A to 0. You can send things in from the left, which corresponds to setting D equals 0. And all of the information about what happens in V is going to be encoded in what's coming out, the B and C coefficients. Okay? And the way to make that sharp is just to notice that the transmission probability, if we compute for this system, for this, assuming this form of wave function asymptotically away from the potential, the transmission amplitude is just C over A squared when you're sending in from the left. And the reflection is equal to B over A squared. This squared is a squared. Wave function amplitude squared. Good. Okay. So to learn about the transmission and reflection coefficients, it's enough, suffices, to compute, to know B and C as a function of A and D. All of the scattering information is in those coefficients B and C for A and D. And here I'm assuming that I'm sending in a monochromatic wave with a single well-defined energy. Okay, I'm sending in a beam of particles with energy E. I don't know where they are, but I sure know what their momentum is. Okay, so it's some well-defined beam of particles with energy E. And these probabilities are going to contain all the data I want. So this is the basic project to scatter. Okay, questions? Well, it's not so much that's a good question. The question is, does the transmission depend only on what you do at the edges? And here's the important thing. The transmission depends crucially on what happens in here. For example, this is an infinitely high barrier. Nothing's going across, right? So the transmission depends on what's in here. But the point is, we can deduce, just by looking far away, we can deduce the transmission probabilities and amplitudes just by measuring B and C far away. B and C far away, okay? So the transmission amplitude is something you measure when very far away. You measure, if I throw something in from very far out here to the left, how likely is it to get out here very far to the right? And that, in order to answer that, if someone hands you the answer to that, they must have solved for what's inside. That's the point. So knowing the answer to that question encodes information about what happened in between. Essentially, this is to see if the step yeah. The potential drops down to drops. Is that going to be like that? Yeah, for simplicity, I'm going to assume that the potential always goes to 0 when we're far away, because that's going to be useful for modeling things like hydrogen and yeah, exactly, carbon, and we're going to use diamonds later in this semester. That'll be useful. But we can repeat this analysis by adding an extra change in the asymptotic potential. It doesn't really change anything important. Yeah.
It looks like the will just be a simple step.
Yes.
Tell from just the probabilities, letting step go up or down.
Ah, excellent. So there's guts. Good. Thank you for that question. That's really great. So already it seems like we can't uniquely identify the potential from the transmission probability if the transition probability is the same for step up or step down, right? So what's missing?
The energy, not the energy out.
But we're working with energy too. So the energy is just a global constant. We'll see what's missing, and what's missing is something called the fission. So very good question. Yeah.
It looks like a good example for
yeah, it is, because it's the ratio of, so that's why I wrote T is here right here. So T is the ratio of J over Ji. And in fact, JT here, JT is equal to C squared times, so this is the probability density. So it's probability density times the velocity. What's the effective velocity here? H bar K2 over M. Whereas J incident is equal to A squared, probability density, times the length of there, the velocity there, which is H bar K1 upon M. So here the ratio of J transmitted to J incident is C squared, norm C squared K2 over norm A squared K1. Exactly, because it's not level. So here they happen to be level, so they'll let the factor cancel. And the only thing that survives is the amplitude. Good question. Yeah?
For a black box example,
yes.
Is it sufficient just to know what's reflected at result situation?
It's not, so for precisely this reason, it's not sufficient to know T. It's not sufficient to know T and R, but of course once you know R, you know T, so you're exactly right that once you know the reflection probability, you know the transition probability. But there's one more bit of information, which we're going to also need in order to specify the potential, which is going to be the phase shift. But you don't need to independently compute B and T, or R and T, you could just compute one. You don't need sensors on, well, you don't need sensors on both sides of the box, but you need to do more than just do the counting problem. We'll see that. Okay, so let's work out a simple example, the simplest example of a barrier of this kind. So we want constant potential. We want a constant potential, and then ending at 0, and we want a constant again from L, and going off to infinity. So what's the easiest possible thing we can do? Step. We're just doing what we've done before twice. So this is an example of this kind of potential. It's sort of ridiculously simple. Well, let's work it out. So we want to scattering. So let's start out. We can either scattering from the left or scattering from the right. Let's start out scattering from the left, so D equals 0. Let's study this problem. So what we know, and let's also note that we have two choices, or we have a choice to make. We can either study energy below the height of the potential, or we can study energy above the height of the potential. And so for simplicity, I'm also going to start with energy greater than the height of the potential, V0. And then we'll do less than V0 afterwards. So it'll be an easy extension of what we've done. Okay, so this will be our first case to study. So we know the form of the wave function out here. It's A e to the x, b e to the minus I kx. We know the form of the potential out here. It's C e to the x and d e to the minus I kx. The only thing we don't know is the form of the potential in here. And in here, it's actually very simple. It's got to be something of the form I think it's called f of g. And notice I did f e to the I k2 k prime x. So I'm calling this k, so we'll just call this k prime x, plus g e to the minus I k prime x. And the reason I chose k prime is because we're working with exponential or energy greater than the potential. So this is a classically loud region. It's an oscillatory domain, but with a different k prime. So here, k squared h bar squared over 2m is equal to e, and h bar squared k prime.
I am watching this at a faster speed, so if you can't understand it, I would just, as I said, Google 804 Spring 2013 for OpenCourseWare, and you will find these lectures. I'm watching lecture 13 right now.
Squared over 2m equals e minus v0, which is positive when e is greater than v0. This analysis will not obtain when e is less than v0. We'll have to treat it separately.
Okay, and then let's just make sure to write this down here. H bar k squared 2m e h bar k2 squared 2m. No, squares here too. Square is equal to e minus v0.
Okay, so now what do? We'll do the same thing. conditions here. That's going to give us 1, 2, 3, 4 matching conditions. We have 1, 2, 3, 4, 5, 6 unknown coefficients. We'll have 2 independent ones. That's great. We set d equals 0 to specify that it's coming from the left and not from the right. That's 5. And then we have normalization, which is 6. So this should uniquely specify our wave function. Yeah? Once we fix e. We have enough conditions. So I'm not going to go through the derivation because it's just an extension of what we did for the first. It's just a whole bunch of algebra. And let me just emphasize this. The algebra is not interesting. It's just algebra. You have to be able to do it. You have to develop some familiarity with it. And it's easy to get good at this. You just practice. It's just algebra. But once you get the idea, don't ever do it again. Once you get reasonably quick at it, learn to use Mathematica, Maple, whatever package you want, and use computer algebra to check your analysis, and use your physics to check the answer you get from Mathematica or Maple or whatever you use. Always check against physical reasonability, but use Mathematica. So posted on the website are Mathematica files that walk through the computation of the transmission and reflection amplitudes and probabilities for this potential. And I think maybe another one, I don't remember exactly. But I encourage you strongly to use computer algebra tools, because it's just a waste of time to spend 3 hours doing algebra calculation. In particular, on your problem set this week, you will do a scattering problem, similar to the scattering problem, or similar to the bound state problem you did last week, the quantum glue problem, which you may be doing tonight, the one you do tomorrow, which is 2 delta function wells and 5 bound states. So that involves a fair amount of algebra. The scattering problem will involve a similar amount of algebra. Do not do it. Use Mathematica or computer algebra just to simplify your life. Okay. Okay, so if we go through and compute so what are we going to do? We're going to use the matching conditions here to determine f and g in terms of a and b. Then we'll use matching conditions here to determine c, d is 0, c in terms of f and g. So that's going to give us an effective constraint relating a and b, leading us to an overall unknown coefficient a, which we'll use for normalization. The upshot of all of which is the answers are that I'm not even going to write down. They're in the notes. Should I write this down? I will skip. So the upshot is that the transmission amplitude, as a function of these k and k prime, the transmission probability, I should say, is 1 over, actually, an evil amplitude. Shoot. So, transmission probability is equal to, and this is a horribly long expression. Okay, transmission probability, which is c over a from squared, is equal to, okay, 4k1, k squared, k prime squared, cosine squared of k prime L, plus k1, k squared, plus k prime squared, sine squared of k prime L, under 4 k squared, k prime squared. Seriously, okay. So we can simplify this out. So you can do some algebra. This is just what you got when you just language the algebra. And now I want to do 2 things. First off, this is horrible. There's a cosine squared, there's a sine squared. Surely we can all be friends and put it together. So let's use some trig. But the second thing, and the more important thing, is I want to put this in dimensionless form. This is horrible. Here we have k's and we have l's, and these all have dimensions. And they're, inside the sines and the cosines is KL. That's good because it says units of normally this says units of length, the dimensions. We'll put everything in dimensionless form. And in particular, what are the parameters of my system? The parameters of my system are, well, there's a mass, there's an h bar, there's a v naught, and then there's an energy, and there's a length L. Okay. So it's easy to make a dimensionless parameter out of these guys, and a ratio of energies, a dimensionless ratio of energies out of these guys. So I'm going to do that. And the parameters I'm going to use are coming from here. I'm going to define parameters g naught squared, which is a dimensionless measure of the depth of the potential. We've actually run into this guy before. 2m L squared v naught over h bar squared. Okay, so this is h bar squared, 1 over L squared is k squared over 2m, so that's an energy. So this is a ratio of the height of the potential to the characteristic energy corresponding to the length scale L. Okay, so the width, there's an energy corresponding to it because you take a momentum which has 1 over that width. You build an energy out of that h bar k squared of 2m, and we have an energy which is the height of the vector. We take a ratio of those. Okay, so that's a dimensionless quantity g naught, and the other dimensionless quantity I want to consider is the ratio of the energy E to v naught, which is what showed up before in our energy plots. So, or in our transmission plot over there, E over v naught. So when we take this and we do a little bit of algebra to simplify our life, again, use Mathematica, it's your friend, the result is much more palatable. It's T for the energy greater than v naught is equal to, still long, but 1 plus 1 over 4 epsilon minus 1, sine squared of g naught square root of epsilon minus 1. And upstairs to 1. Okay? So remember, this is only valid for E greater than V naught or only epsilon greater than 1. And I guess we can put an equal in. So when you get an expression like this is as easy as you're going to make this expression. It's not going to get any easier. It's 1 over a sine times a function plus 1. There's really no great way to simplify this. So what you need to do when you get an expression like this is try to figure out what it's telling you. the useful thing to do is to plot it. So let's just look at this function and see what it's telling us. So let's plot this t as a function of epsilon, and for some fixed g naught. Okay. And keep in mind that this only makes sense for e greater than v naught or for epsilon greater than 1. So here's 1. And we're going to remain agnostic as to what happens below 1. And just for normalization, we know that the transmission probability cannot be greater than 1, so it's going to be between 1 and 0. So here's 0 and 0. Okay, so we're remaining agnostic about this for a moment. So let's start thinking about what this plot looks like. First off, what does it look like at 1? So when epsilon goes to 1, this is going to 0. That's bad because it's in the denominator. But upstairs, this is going to 0. And sine squared of something when it's becoming small goes like, well, sine goes like that thing. So sine squared goes like this quantity squared. So sine squared goes like g naught squared, which goes like 1 over. This is going like g naught squared, epsilon minus 1 square root quantity squared, which is epsilon minus 1. So this is going to 0, and this, the denominator, is going to 0 exactly in the same way. Epsilon minus 1 from here, epsilon minus 1 downstairs from here. So the epsilon minus 1 precisely cancel. From the sine squared, we get a g naught squared, and from here we get a 4 epsilon. So we get 1 plus g naught squared over 4 epsilon. But 4 epsilon, what was epsilon here? 1, right? We're looking at epsilon goes to 1, so this is just g naught squared over 4. So the height, the value of t, so we're not looking at here, but at energy is equal to v naught or epsilon is equal to 1, we know that the transmission amplitude is not 0, but it's also strictly smaller than 1, which is good, because if it were 6, you'd be really worried. So g naught squared is 0, what do we get? 1, fantastic, there's no barrier, we just keep right on going through, perfect transmission. If g naught is not 0, however, the transmission is suppressed, like 1 over g naught squared. So, what does this actually look like? Well, some value. Okay, and what is this value? It's just 1 over 1 plus 1/4 g naught squared. Cool? Okay, and now what happens, for example, for very large epsilon? Well, when epsilon is gigantic, sine squared of this is, well, sine squared is oscillating rapidly, so that's kind of worrying. If this is very, very large, this is a rapidly oscillating function. However, it's being divided by roughly epsilon squared. So something that goes between 0 and 1 divided by epsilon squared, as epsilon gets large, becomes 0. And if we get 1 over 1 plus 0, we get 1. So for very large values, it has to go to 1. So naively, it's going to do something like this. However, there's this sine squared, and in fact, this is exactly what it would do if we just had the 1 over epsilon times some constant. But in fact, we have the sine squared. The sine squared is making a wiggle. And the frequency of the wiggle is g naught, except that it's not linear in epsilon, it's linear in square root of epsilon. So as epsilon gets larger, the square root of epsilon is getting larger less than linearly. Yeah? So what that's telling you is if you looked at root epsilon, you would see it with even period. But we don't have root epsilon. We're applying this as a function of epsilon, so it's not even period, it's getting wider and wider. Meanwhile, there's a nice fact about this. For special values of epsilon, what happens to sine squared? It goes to 0. What happens when it's 0? Yeah, t is 1. So every time sine is 0, I mean, for sufficient values of root epsilon is a multiple of pi determined by g naught, transmission goes to 1, it becomes perfect. So in fact, instead of doing this, what it does is it does this. So let's check that I'm not lying to you. So let me draw it slightly different. So to check, so it's going to 0, and the period of the 0 is getting further and further along. That's because this is square root, not squared. So epsilon has to get much larger to hit the next period. That's why it's getting larger and larger spacing. However, the amplitude goes down from 1, that's when this gets largest. Well, at large values of epsilon, this is suppressed. As we get epsilon is larger and larger, this deviation becomes smaller and smaller. Okay? So that's what this plot is telling us. This plot is telling us a bunch of things. First off, we see that at large energies, we transmit perfectly. That makes sense. This was a finite Heidegger. Large energies, we don't even notice. Tells you at low energies, well, we don't know yet what happens at very low energies. But at reasonably low energies, the transmission is suppressed. And if you sort of squint, this roughly does what we expect from the step barrier. However, something really special is happening at special values of epsilon. We're getting perfect transmission. We get perfect transmission at these points. T is equal to 1. Perfect. Scar. Happy with a good nose. I don't know. Do you know this? Perfect transmission at all these points. So this is just with the question of why. Right? Why the perfect transmission? What's the mechanism making transmission perfect? But it also does something really lovely for us. Suppose you see a spectrum, you see a transmission amplitude or transmission probability that looks like this. You may get crappy data. You may see that it's smudged out and you see all sorts of messy stuff. But if you know that the perfect transmission is some particular epsilon 1, there's more perfect transmission than epsilon 2, more perfect transmission than epsilon 3, and they scale, they fit to this prediction, what do you know? That you've got a finite height barrier. That's probably pretty well approximated by square step. Yeah? So in your problem set, you're going to get experimental data. And you're going to have to match to the experimental data. You're going to have to predict something about the potential that created a particular transmission probability. Where these resonances are, where the constant transmission is going to be very useful for you. Yeah? A very good question. So let me turn around to you. Can you orchestrate a potential that gives you the same thing? That's an interesting empirical question. So on the problem set, you'll study a double potential. So the question was, how do there's another potential between T100? That's what we don't. There's another potential. In fact, you can do all sorts of things to negative potential. It's very arbitrarily close to it. It could be an arbitrarily similar profile. But the natural, so if they're significantly different, how different do they look? So on the problem set, so then the students say, well, I don't know, what about a double potential? So in fact, we'll be only a double potential on the problem set. Okay, a good question, and we certainly haven't proven anything like this is the only potential that gives you this transmission. What we can say is if you get transmission that looks like this, it's probably pretty reasonable to say it's probable model, right? We seem to be reproducing the data reasonably well. So it's not a proof of anything, but it's a nice model, and we're physicists, we build models. We don't tell you what's true. We tell you what are good models. If here's our walk up and he says like, here's the truth, punch in the gut. It's not how it works. Experimentalists, on the other hand, I'll just touch them too. Field models. Okay. So this leaves us with an obvious question, which we've answered this in the case of energy greater than the potential. What about the case of the energy less than the potential? So we haven't filled out that part of the graph. Let's fill out that part of the graph. What happens if the energy is less than the potential? And for this, I'm going to use the trick that I mentioned earlier, that look, if the energy is less than the potential, that just means that in the intervening regime, in here, instead of being oscillatory, it's going to be exponentially growing damped, because we're in classically dissimilar regime. So if the energy is less than the V0, here we have, instead of ikx, we have minus alpha x, and instead of minus ikx, we plus alpha x. So if you go through that whole analysis and plug in those values for the k's, for the k prime, the answer you get is really quite nice. We find that t for energy less than V0 is equal to, and it's just a direct analytic continuation of what you get here, 1 plus 1 over 4 epsilon 1 minus epsilon. So epsilon is less than 1 now. 1 sinh squared of G0 1 minus epsilon under 1. Okay. So now this lets us complete the plot. And you can check, it's pretty straightforward, that because sinh again. Okay, so now this lets us complete the plot. And you can check, it's pretty straightforward, that because sinh again goes like its argument at very small values of its argument, again we get G0 squared 1 minus epsilon. Sorry, this should be square root 1 minus epsilon. Really? It's a 10%? Oh, no, it's in there. Okay, good. So again, we get G0 squared 1 minus epsilon cancels, and we get 1 over 4 G0 squared, which is good, because if they disagree, we get in trouble. Okay. So they agree, but the sinh squared is just a strictly, or that function is just a strictly decreasing function as we approach epsilon goes to 0, goes mostly to 0. So this is what we see. We see an exponential region, and then we see oscillations with resonances where the period is getting wider and wider.
I'm just going to redraw the graph here.
But this should trouble you a little bit. Here, what are we seeing? We're saying, look, if we have a barrier, and we send in a particle with energy way below the barrier, that's kind of troubling. If we send in a particle with energy way below the barrier, there's some probability that it gets out, that it goes across. So for E less than V0, classically no transmission, we get transmission. Now, do we get resonances when E is less than V0? No, that's an interesting thing. We'll talk about resonances and where they come from, and we'll talk about the more generalized notion of an S vectors in the next lecture. But for now, I just want to say a couple of things about it. So I want to ask, so this is called tone, this transmission across the barrier, so across a disallowed barrier, classically disallowed barrier. So this transmission across classically disallowed barrier is called tunneling. And just a quick thing to notice is that if we hold E fixed, and we vary L, we vary the width of the barrier, how does the tunneling have to depend on the width of the barrier?
All right, let's see if I can answer that. I'm assuming it's going to go up, but where do we have E? G is proportional to this L squared. So as L gets smaller, this sine H is going to go up. Sine H squared is going to go up. So this is going to be sine H squared. So it's this term that gets, it's the square root of that. This is the G0. So it's proportional to L. And sine, hyperbolic sine goes like this, right? So this is going higher, so it should go up and up, right?
At fixed energy, if we vary the width of the barrier, which is only contained in G naught, how does the transmission amplitude vary? And we find that for large L, for L much greater than 1 for typical scaling problem, the tunneling amplitude goes like e to the minus 2 alpha L, where alpha just depends on the energy in the pendulum. So what we see is that the probability of transmitting of tunneling through a wall depends on the width of that wall, and it depends on it exponentially. The wider the wall, the exponentially less likely you are to tunnel across it. And this fits the simulation we ran, where we saw that tunneling through a very thin wall was actually quite efficient. And we also saw that tunneling across a wall can have resonant peaks at special values. It transmits perfectly. We saw that in simulations. So at this point, I can't just tell you a very short story. I have a very good friend. Who's not a physicist, but who is a professor at MIT. A smart person, and very smart. She's one of the smart people I know. And she broke her ankle. She's always losing stuff. She's constantly losing stuff. And she broke her ankle, and she was going to the rehab place. She parked her car right in front of the rehab place. And she parked her car right in front because she had a broken ankle, and she didn't want to have to walk all the way to get the car. And she was right in front. She went in. She did her 2 hours of rehab, and she came outside, and her car was gone. And she's always misplacing her car. She's always misplacing her keys. She's always losing everything. But this time she knew where it was, and it wasn't there. And so first she thought, oh crap, my car's been stolen. Like, this is just how annoying. I've got a broken ankle in my car. But she looks around, and there's her car on the other side of the street pointing the opposite direction. And she's like, finally. And she was explaining this to me and a friend of mine who's also a physicist. She said, finally, I knew I had just incontrovertible proof that quantum effects happen in macroscopic objects. My car tunneled across the street. At this point, of course, my friend and I were just like dying of laughter. She said, my car tunneled across the street. And here's the problem. I couldn't tell anyone. Because if I told anyone, they would know that I was crazy, right? Clearly I'm crazy. Because, surely, I lose my stuff all the time, but surely it's just got misplaced. So I went home, and I got home, and I was sitting down with my partner and her daughter, and I was burning up inside because I wanted to tell them this crazy thing happened. I know quantum mechanics. It happens. And I couldn't tell them anything, so I was just fidgeting and dying. And finally, my daughter said, Mom, didn't you notice that we moved the car across the street? See you next time.
All right, let's go on to the next one. Well, people are saying, oh, did this not update? Oh, boy. Sometimes I'm not sure whether it's updating my thing properly here. So I don't know whether you guys got any of that lecture. Hopefully we got some of those notes there. Pavel was asking how my pencil never comes out. It's because I have 4 and I sharpen them all before my class starts. So, well, I apologize if the video wasn't present for that one. I think maybe I forgot to send it to live when I switched over to that view. Little live streaming glitches in this whole process. I'm still getting used to it, so you guys will have to bear with me here. All right, let's try lecture 14.
Following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
So today we're going to do our last lecture on scattering in quantum mechanics and 1D quantum mechanics. And we're going to introduce some powerful ideas from Aphasia and the S matrix, and we'll use them for good. Before we get started, questions from last time. Just now, it's a band called Saint Germain. It's actually a guy, but he refers to himself as a band called Saint Germain. Anyway, it's from an album I think called Traveler. So these questions. Anyone? Okay, good. Well, bad actually. I'd much prefer if you had questions, but I'll take it as a sign of knowledge, competence, and mastery. Okay, so last time we talked about scattering past a barrier with some height L and some height V, which I think we call V naught. And we observed a bunch of nice things about this. First off, we computed the probability of transmission across this barrier. The probability of transmission across this barrier is a function of the energy. And it had a bunch of nice features. First off, it asymptoted to 1 at high energies, which makes sense. Things shouldn't really care if you have a little tiny barrier. It went to 0 at 0 energy. I don't know how, I think we should all find out. If you get extremely low energy, you're just going to bounce off this very hard wall. In between, though, there's some structure. In particular, at certain values of the energy corresponding to certain values of the wave number in the barrier region, at certain values of the energy, we saw that the transmission was perfect. Oops, this should have been here, sorry. The transmission was perfect at special values of the energy, and that the reflection at those points was 0. You transmitted perfectly. But meanwhile, the reflection, which is 1 minus the transmission, hit maxima at special points, and those special points turn out to be half-integer shifted away from the special points for perfect transmission. So at certain points we have perfect transmission, at certain points we have extremely efficient reflection. And so one of our goals today is going to be to understand this physics, the physics of resonance in scattering off of a potential, okay? So the asymptotes we understand, classically that makes sense, but classically this is a really weird structure to see. And notice that it's also not something that we saw when we looked at scattering off of a simple step. When we looked at a simple step, what we got was something that looked like a 0, and then this, right? There was no structure, it was just a nice simple curve. So something is happening when we have a barrier as opposed to a step. So our job is going to be, in some sense, to answer why are they so different. Before I get going, questions about the step barrier? Yeah?
That little tiny interior graph, is that scale?
Oh, sorry. This one? That was the transmission. Sorry, I should have drawn it separately. That was the transmission as a function of energy across a single step. And so that looked like this. Exactly. Sorry. So I just meant to compare the two. I just want to think of those two different systems. In this system, we have the transmission curve is a nice simple curve. It has no structure. In the case of the step barrier, we get non-zero transmission at low energies instead of going to 0, and we get this resonance structure. So just for contrast. Okay, so before going into that in detail, I want to do one slight variation of this problem. I'm not going to do any of the computations. I'm just going to tell you how to get the answer from the answers we've already computed. So consider a barrier, or a square well. You guys have solved the finite square well in your problem sets. Consider a finite square well again of width L and of depth minus V naught. So it's the same thing with V goes to minus V. Okay. And again, I want to consider scattering states. So I want to consider states with positive energy above the asymptotic potential. Now, at this point, by now, we all know how to solve this. We write plane waves here, we solve them, and plane waves in between, we solve the potential in each region where it's a constant, and then we impose continuity of the wave function and continuity of the derivative of the wave function at the matching points. Right? So we know how to solve this problem and deduce the transmission and reflection coefficients. We've done it for this problem, and it's exactly the same algebra. And in fact, it's so exactly the same algebra that we can just take the results from this one and take V minus V, and we'll get the right answer. You kind of have to. So if we do, what we get for the transmission probability, and now to the transmission probability for a square well, and again, I'm going to use the same dimensionless constants. G naught squared is equal to 2m L squared over h bar squared times V naught. This is 1 over an energy. This is an energy. This is dimensionless. And the dimensionless energy, epsilon, is equal to E over V. To express my transmission probability, life is better when it's dimensionless. So T, the transmission probability, is again, it's one of these horrible 1-overs. 1 over 1 plus 1 over 4 epsilon plus 1. Good. Sine squared of G naught square root of epsilon plus 1. And this is again the same. So if you remember last time, you can see what we got last time by now taking V minus V again. That takes epsilon to minus epsilon. So we get epsilon 1 minus epsilon, or epsilon minus 1 picking up the minus sign from this epsilon. And here we get 1 minus epsilon instead of 1 plus epsilon. That's precisely what we got last time. So if you're feeling punchy at home tonight, check this. In some sense, you're going to rewrite it on the problem set. Okay, so it looks basically the same before. We have a sine function downstairs, which again will sometimes be 0. The sine will usually be 0 when its argument is multiplied by pi. And when that sine function is 0, then the transmission probability is 1 over 1 plus 0. It's also known as 1. Transmission is perfect. So we can get a resonance structure. And it's in fact exactly the same plot, or almost exactly the same plot. So I'm going to plot transmission. Well, let's go ahead and do this. Transmission probability as a function, again, of the dimensionless energy. And what we get is, again, oops, not very well drawn. Resonances where transmission goes to 1. Thanks for my good artistic skills. Points where the resonance, or where the reflection hits a local maximum. But we know one more thing about this system, which is that in addition to having scattering states, whose transmission probability are indicated by the plot, we know we also have, for negative energy, bound states. Right? Unlike the step barrier, for the step well, we also have bound states. So here's the transmission curve. But I just want to remind you that we have energies, at special values of energies, we also have bound states. And precisely what energies depends on the structure of the well and the depth. But if the depth of the well is, say, V naught, so this is minus 1, we know that the lowest bound state is always greater energy than the bottom of the well. Cool? So epsilon, remember, is E over V naught. And in the square well of depth V naught, the lowest bound state cannot possibly have energy lower than the bottom of the well. So its epsilon must have epsilon greater than 1, or minus 1. Cool. Anyway, this is just a reminder that there are bound states. And think of this like a gun put down on a table in a play in Act 1. It's not dramatic. So it will show up again. It'll come back and play well with us. So I want to talk about these resonances. Let's understand why they're there. So there are a bunch of ways of understanding why these resonances are present. And let me just give you a couple. So first, a heuristic picture, and then I want to give you a very precise computational picture of why these resonances are happening. So the first is, imagine we have a state where the transmission is perfect. What that tells you is KL is a multiple of pi. So in here, so this is the distance L of the well, in here the wave is exactly 1 period, or because KL is equal to a multiple of pi. So if KL is pi, whoops, I think I want to. So let me simplify my life and consider the case KL is 2 pi. So when the wave comes through and becomes, oh, I know why, shoot. So for this, sorry, 4 pi. So I switched notations for you. I was using in my head with the well is 2L from for reasons you'll see on the notes. But let's ignore that. Let's focus on these guys. So consider the state a configuration and energy such that in the well, we have exactly one period of the wave function. That means that the value of the wave function at the two ends is the same, and the slope is the same. So whatever the energy is out here, if it matches smoothly, continuously, and its derivative is continuous here, it will match smoothly and continuously out here as well with the same amplitude and the same period inside and outside. Right? The amplitude is the same, the phase is the same. That means this wave must have the same amplitude and the same period. Well, it has to have the same period, it's the same energy. It must have the same amplitude and the same slope at that point. And that means that this wave has the same amplitude as this wave. The norm squared is the transmission probability. Norm squared of this divided by the norm squared of this. That means the transmission probability has to be 1. What would have happened had the system, instead of being perfectly periodic inside the well? Well, let me leave that out. So we have. So let's do it as this. Oh shoot! I'm even getting the quality of wave functions wrong. Okay, start at the top, go down, and then it's got a lower. It's deeper inside the well. So the amplitude out here, the difference in energy between the energy and the potential is less, which means the period is longer and the amplitude is greater. But it's the way I've drawn it. It's got a particular value. It's got zero derivative at this point. So it's got 2. Okay, good. So there's our wave function. Same thing out here. The important thing is the amplitude here has to be the same as the amplitude here, because the amplitude and the amplitude of the phase were exactly as if there had been no intervening region. Do you agree with that? By contrast, if we look at a situation where inside the well it was not the same amplitude, so for example, something like this came up with some slope which is different and the value which was different, then this is going to match onto something with the same period but with a different amplitude than it would have over here. Same period because it's got the same energy but a different amplitude, because it has to match on with the value and the derivative. So you can think through this and pretty quickly convince yourself of the necessity of the transmission amplitude being 1 if this is exactly periodic. Again, if this is exactly one period inside, you can just imagine this is gone and you get a continuous wave function. So the amplitude and the derivative must be the same on both sides. It's as if there was no barrier there. And when the phase is not the same, when the wave function doesn't have exactly one period inside the well, you can't do that. So the amplitudes can't be the same on both sides. Okay? But that's not a very satisfying explanation. That's really an explanation about solutions to the differential equation. I'm just telling you properties of second-order differential equations. Let's think of a more physical, more quantum mechanical explanation. Why are we getting these resonances? Well, I want to think about this in the same way we thought about the boxes in the very first lecture. Suppose we have this square well, and I know I have some amplitude here. And I want to know, I've got a wave function, it's got some amplitude here, it's got some momentum going this way, some positive momentum. And I want to ask, what's the probability that I will scatter past the potential, let's say to this point right here, just on the other side of the potential? What's the probability that I will scatter across? Well, you say, we've done this calculation. We know the probability to transmit across this step potential. We did that last time. So it's T step. And we know the probability, we know what happens to the phase of the wave function, or sorry, we know the probability of scattering across this potential step, and that's transmission up. And so the probability that you transmit from here to here is the probability you transmit here first, and then the probability you transmit here, right? The product of the probabilities. Sound reasonable? Okay, let's vote. How many people think that this is equal to the transmission probability across the potential well? Any votes? You have to vote one way or the other. No, it is not. How many people vote? Okay, yes it is. Okay, the no's have it, and that's not terribly surprising, because of course D's have no resonance structure, so where did that come from? It's just that thing squared. Right? So that probably can't be it. But here's the bigger problem. Why is this the wrong argument? Yeah, exactly, there's reflection, but that's only one step in the answer of why it's the wrong answer. Why else? That's true, but I just want the probability. If I got here with positive momentum, I'm eventually going to get out to infinity, so it's the same probability. Because it's just an easy x. The wave function is just an easy x. So the probability is going to be the same. Other reasons.
The width of the well is very important, but the first one is more.
Exactly, that's also true. So far the reasons we have are, we need the width of the well doesn't appear. That seems probably wrong. Okay. The second is, it's possible you could have reflected. We haven't really incorporated that in any sort of way. That's absolutely true. There are other ways to transmit. So you could transmit, then you could reflect. So we could transmit, then reflect, and reflect again, and then transmit. So we could transmit, reflect, transmit. What else? Do probabilities add in quantum mechanics? And when you have products of events, you have probabilities multiply. What adds in quantum mechanics? The amplitude, the wave function. We do not take the product of probabilities. What we do is we ask, what's the amplitude to get here from there? And we take the amplitude norm squared to get probability. Right? So the correct question is, what's the amplitude to get from here to here? How does the wave function of the amplitude change as you move from here to here? And for that, think back to the two-slit experiment and think back to the boxes. We ask the following question. The amplitude that you should transmit across this well has a bunch of components, is a sum of a bunch of terms. You could transmit down this well, down this well. Inside here, you know your wave function is e to the I k prime L, our thing called K2L. Yes, K2X. And in moving across the well, your wave function evolves by e to the I K2L. And then you can transmit again with some transmission amplitude. So this would be the transmission down times e to the I K2L times the transmit up. As we saw last time, these are the same, but I just want to keep them separate so you know which one I'm talking about. So this is a contribution. This is something that can contribute to the amplitude. Is it the only thing that can contribute to the amplitude? No, what else could contribute? That, right? So if you get from here to here, I could transmit, evolve, transmit. I could also transmit, evolve, reflect, evolve, transmit. So there's also a term that's T, e to the ikl, R, e to the minus ikl, R, e to the ikl. Sorry, e to the plus ikl. We're increasing the evolution of the phase. And then transmit finally at the end. And these Ks are all K2s, K2, K2. But I could have done it many times. But notice that each time what I'm going to do is I'm going to transmit, reflect, transmit, or transmit, reflect, transmit. So I'm always going to do this some number of times. I do this once, I do this twice, I do it thrice. This gives me a geometric series. This is T e to the ik2n. T times 1 plus this quantity squared. That's a geometric series. 1 over 1 plus this quantity squared. Or sorry, 1 minus, so it's a geometric sum. And what is this quantity? Well, it's r squared. And remember, the r's in both directions are the same, so I'm just going to write it as r squared. E to the 2i. R squared. The real number, but yeah, absolute value on. Anyway, it's going to simplify. E to the 2i, k2l. So this is our prediction from multiple bounces. What we're doing here is we're taking seriously the superposition principle that says, given any process, any way that process could happen, you solve the amplitudes and the probabilities of the norm squared. If we have a source and we have 2 slits, and I ask you, what's the probability that you land here? The probability is not the sum of the probabilities for each individual transit. The probability is the square of the amplitude, where the amplitude is the sum, amplitude top plus amplitude bottom. Here, there are many, many slits. There are many different ways this could happen. You could reflect multiple times. Ever go with that? No. By the same token, we could have done the same thing for reflection. But let's take the transmission for the moment. This is what we get for the transmission. And again, the transmission amplitudes across the step, as we saw last time, are the same. So this is in fact t squared. And this gives us a result for transmission down the potential well. And if we put in the factors of, if we use what if we use what the reflection and transmission amplitudes were for our step wells, the answer that this gives is 1 over e to the I k2l minus 2i upon the transmission for a step times sine of k prime l, or sorry, k2l. Now this isn't the same as the probability that we derived over here. But that's because this isn't the probability, this was the amplitude. We just computed the total amplitude. To get the probability, we have to take the norm squared of the amplitude. And when we take the norm squared, what we get is 1 upon 1 plus 1 over 4 epsilon, epsilon minus 1, or plus 1, sine squared of g naught root epsilon plus 1. We get the same answer. Sorry? This is inequality. Oh, sorry. Sorry. Thank you, Martin. We get that the transmission probability when we take the norm squared of the amplitude, thank you, is equal to this, which is the same as we got before. Thanks. Okay. So this is, to me, this is very simple. Yeah, please. Kale equals pi doesn't work. It does. You just have to be careful what kale. Okay, sorry. What do I? Because I'm an idiot. Because I got a factor of 2 wrong. Thank you. Thank you, math. Thank you. Answer analysis is a wonderful thing. Okay. So this gives us something really nice for us. Why are we getting resonance at special values? Why are we getting resonance at special values of the energy? What's happening? Well, in this process, in this quantum mechanical process of multiple interactions, multiple scatterings, there are many terms in the amplitude for transmitting. There are terms that involve no.
I think I got a mistake wrong here. I don't think this is true. I'm going to cross it out right now so I don't get confused later.
There are terms that involve 2 reflections. There are terms that involve 4 reflections. And they all come with an actual magnitude and a phase. And when the phase is the same, they add constructively. And when the phases are not the same, they interfere. And when the phases are exactly off, they interfere destructively. And that is why you're getting a resonance. Multiple terms in your superposition interfere with each other. Something that does not happen classically. Classically, the probabilities are products. Quantum mechanically, we have superposition. Probabilities are the squares of the amplitude. And we get interference effects and probabilities. Cool? So to me, this is a nice, sort of glorious version of the 2-slit experiment. And we're going to pop up again into it later when we talk about the physics of solids in the real world. Okay. Questions? Yeah. Yeah, what's special about that? So what's special about that is, so at this point where KL is in pi, when KL is in pi, we get perfect transmission. When KL is equal to n plus 1/2 pi, the reflection is as good as it gets. Okay, so what that's really doing is it's saying when is this largest, locally largest. Okay? So that's these special points when the transmission is as small as possible, which means reflection, which is when the transmission probability is as large as possible. And you can get that again from these expressions. Other questions? Okay. So solving. So I want to think a little more about these square barriers. And in particular, in thinking about the square well barrier, what we've been talking about all along are monochromatic wave factors. We've been talking about plane waves, just simple easy IKX. But you can't actually build, you can't put a single particle in a state which is a plane wave. Right? It's not normalizable. What we really mean at the end of the day when we talk about single particles is we put it in some well-localized wave packet, which at time zero, let's say, is a position x naught, or maybe, well, x naught, which in this case is negative, and which has some well-defined average momentum k naught. I'll say it's the expectation value momentum in this wave packet. And the question we really want to ask when we talk about scattering is what happens to this beast as it hits the wave, as it hits the barrier, which I'm going to put the left-hand side at 0 and the right-hand side at L, so let the depth be minus v naught again. What happens is this incident wave packet hits the barrier and then scatters off. Well, we know what would happen if it was a plane wave, but a plane wave wouldn't be localized. So this is the question I want to ask, and I want to use the results we already have. Now, here's the key thing. If we had considered, to begin with, just a wave packet for a free particle centered at x naught and with momentum k naught, okay, just for a free particle, we know how to write this, and if this is, we can put the system, for example, we can take our wave function at time 0 to be a Gaussian, so normalization times e to the minus x minus x naught squared over 2a squared, and we want to give it some momentum k naught, and you know how to do that after the last problem set, e to the I k naught x. Can we go that? So there's our initial wave function.
I'm just going to write that down. Squared. Very hard to write this all in the exponent. I'm just going to put the e a little bit lower.
And we want to know how to evolve in time, and we know how to do that. To evolve in time, we first expanded in energy eigenstates. So psi of x naught is equal to, well, the energy eigenstates in this case are plane waves, dk e to the ikx over root 2 pi times some coefficients, f of k, the expansion coefficients. But these are just the Fourier transform of our initial Gaussian wave packet. And we know what the form of f of 0 is. F of k is equal to, well, it's a Gaussian with 1 pi alpha, e to the minus k minus k naught, because it had momentum k naught. So it's centered around k naught squared over 2 times a squared, and then it goes upstairs. And the position of the initial wave packet is encoded in the Fourier transform. And I'm going to put normalization here, which I'm not going to worry about, with an overall phase e to the I minus I k x naught. So in just the same way that adding on phase e to the I k naught x in the position space wave function tells you what the expectation value of momentum is, tacking on the phase. We can get this from Fourier transform. Tacking on the phase e to the I k x naught tells you in the Fourier transform tells you the center point, the central position of the wave packet. Okay, so this you did on the problem set. This is a trivial momentum space version of the same thing. So here's our wave packet expanded in plane waves, which are energy eigenstates. And the statement that these are energy eigenstates is equivalent to the statement that under time evolution they do nothing but rotate by a phase. So if we want to know the wave function is a function of time, psi of x and t is equal to the integral dk, the Fourier mode, f of k. I'll write it out. Actually, I'm going to write this out explicitly. F of k. 1 over root 2 pi, e to the I kx minus t. Where omega, of course, is a function of k, it's a free particle. So for our free particle, h bar squared, omega squared, or sorry, h bar squared, q squared, 0.2m is equal to h bar omega. Okay? So we've done this before. But now what I want to do is I want to take exactly the same system and I want to add at position 0 a well of depth v naught and width L. How is our story going to change? Well, we want our initial wave packet, which is, up to us to choose. We want our initial wave packet to be the same. We want to start with a Gaussian far, far, far away from the barrier. We want it to be well localized in position and well localized in momentum space. Not perfectly localized, of course. The finite Gaussian to satisfy the uncertainty principle, but it's well localized. So how does this story change? Well, this doesn't change at all. It's the same wave function. However, when we expand in energy eigenstates, the energy eigenstates are no longer simple plane waves. The energy eigenstates, as we know, for the system, take a different form. For the square whale and positive energy scattering states, the plane wave of the energy eigenstates, which I will label by k, just because I'm going to call E is equal to a squared k squared upon 2m, which is the energy, the energy constant, which is the k asymptotically far away from potential. The wave function I can write as 1 over root 2 pi times e to the ikx when we're on the left-hand side, but left being on the left-hand side is equal to multiplying by theta.
Energy eigenstates.
Function of my f minus x. This is the function which is 0 when its argument is negative and positive when its argument is, and 1 when its argument is positive. Plus, we have a reflected term.
I just need to hear him explain this function once more.
The wave function I can write as 1 over root 2 pi times e to the ikx when we're on the left-hand side. But being on the left-hand side is equivalent to multiplying by a theta function of my f minus x. This is the function which is 0 when its argument is negative and positive when its argument is, and 1 when its argument is positive. Plus, we have the reflected term, which has an amplitude r, which is again a function of k. This is the reflection amplitude, also known as c upon a, e to the minus ikx. Again, on the left-hand side, theta minus x. Plus, a transmission amplitude, whose norm squared is transmission probability, e to the ikx, when we're on the right. Theta of x. So this is just a slightly different notation than what we usually write, with left and right separated.
So let's see if we can understand this, because this is going over my head a little bit. We've got the energy eigenstates with a thing that when we take the energy operator of it, we'll just return a coefficient. Now, why is this? Why is this going to be the energy eigenstate? We have
So what we want to do now is we want to decompose our wave function in terms of the actual energy eigenstates.
So why was this the energy eigenstate? I'm just going to put a note here. Maybe it'll show up later in the lecture.
And so the way we're going to do that, and having done that, having expanded our wave function in this basis, we can determine the time evolution the following way. First, we compute, we expand the wave function at time 0 as an integral dk, and I'm going to fold the root 2 pi out. And we have some Fourier transform, which I'm not going to call f tilde because it's slightly different than the f we used before, but it's what the expansion coefficients have to be. F tilde of f tilde of k times this beast, phi sub k. Phi of k. Good. And let me actually write this out in terms of let me actually take this product and write it out in terms of the 3 terms. So those 3 terms are going to be f of k tilde e to the ikx theta minus x plus f tilde r e to the minus ikx theta minus x plus f tilde t e to the ikx theta of x. So
over minus alpha. Oh no, I remember. Okay. Yeah, kx. Okay. T.
let's look at these terms. This is this wave function now. Oh, and sorry. Finally, we want to look at the time evolution, but this we started out as a superposition of states with definite energy labeled by k. So we know the time evolution is e to the ikx minus omega t, e to the I minus ikx plus omega t, that's minus I omega t, and kx minus omega t. So we can immediately, from this time evolving wave function, identify these 2 terms as terms with a central peak moving to the right, and this a central peak moving to the left, x plus omega t. Everyone cool with that? Questions? Okay. Yeah. How that? Sorry. Say again. How the top equation led to this, or just where this came from? Oh, good. Okay, so this is just a notational thing. So usually when I say a phi sub k is equal to, on the left, e to the ikx with some overall amplitude, a, let's say 1 over 2 pi, e to the ikx plus c over a e to the minus ikx. Right, on the left. And I'm just going to call this, because this is the reflected wave, I'm just going to call this r. Okay, and then on the right, we have e to the ikx. There's only a wave traveling to the right, and the coefficient is the transmission amplitude. So this is what we normally write. But then I'm using the function, the theta function, so-called theta function. Theta of x is defined as 0 when x is less than 0, and 1 when x is greater than 0. Okay, so this is a function 1. So this allows me, using theta function, allows me to write this thing as a single function without having to goose around
Okay.
Lots of terms. Is that cool?
Just taking one step because otherwise we should have something to do.
Fantastic. Excellent. Thank you so much. So here what I want to do is, thank you. What I want to do is I want to think of the wave function. So this is a good description when the particle is far, far away. And this is a good description when the particle is not in the potential. So I want to just imagine this. Sorry, thank you. I totally glossed over this step. I want to imagine this as a potential where all of the matching is implemented at x equals 0. Okay. So when I write it in this fashion. But the better way to, another equivalent way to think about this is a good description of the wave function when we're not inside the well. So for the purposes of the rest of the analysis that I'm going to do, this is exactly what the form of the wave function is when we're not inside the well. Okay. And then let's just not use this to ask about questions inside the well. When I write it in this theta form, or for that matter, when I write it in this form, this is not the form. What I mean is left of the well and right of the well. And inside t e to the I kx. Inside, it's doing something else.
So that's a good example of why waiting to go through things instead of pausing the lecture sometimes makes sense, because sometimes they explain the thing you're confused about.
But we don't want to ask questions about it. Okay. That's just going to simplify my life. Yeah. It's the square root of capital T, but you've got to be careful because there can be a phase. Remember, this is the amplitude, and what it really is this reflection is B over A, and these guys are complex numbers. And it's true that B over A norm squared is the transmission probability. But B over A has a phase, and that quantity I'm going to call T, and we'll interpret that in more detail in a few minutes. Okay. So it's of this form, and I just want to look at each of these three terms. And in particular, I want to focus on them at time 0. So at t equals 0, what does this look like? Well, that first term is integral dk of f of k e to the I kx minus omega t. Okay, theta minus x. Notice that theta minus x is independent of k. It's independent of the k integral. So this is just a function times theta minus x. And this function was constructed to give us the initial Gaussian. So this is just, and this was at t equals 0. So this is just our Gaussian at position x naught, centered around value k naught at time equals 0. Theta f minus x. Okay. This is just saying that, at position x, of x naught. So all this function is this is the Fourier transform of our Gaussian, and we're undoing the Fourier transform. So this is just giving us our Gaussian back. And as long as the particle is far away from the well, so here's the well, and here's our wave packet, that theta function is totally irrelevant because the Gaussian makes it 0 away from the center of the Gaussian anyway. And so, just as a quick question, if we look at this as a function of t, so we put back in the minus omega t, so if we put back in the time dependence, this is a wave that's moving to the right, and we need to to be more precise about that. What does it mean to say it's a wave moving to the right? Well, this is an envelope on this set of plane waves, and the envelope, by construction, was well localized around position x, but it was also well localized in momentum. And in particular, the Fourier transform is well localized around momentum k naught. And so using the method of stationary phase, or just asking where is the phase constant stationary, we get that the center, the peaks, the central peak of the wave function satisfies the equation ddk naught. If you're not familiar with stationary phase, let the recitation instructors know, and they will discuss it for you. So the points of stationary phase of this this superposition of this wave packet lie at the position ddk naught of kx. Ddk of kx minus omega of kt, evaluated at the peak k naught of the distribution. But ddk of kx minus omega t is, for the first term, x, and for the second term, ddk of omega, well, we know that omega, we're in the free particle regime. Omega, where did it go? Well, we all know what it is. It's h bar k squared upon 2m. We take a derivative with respect to k, we get h bar k over m, the 2's cancel. So x minus h bar k over m t. And a place where this phase is zero, where the phase is stationary, moves over time as x is equal to h bar k over m p. But h bar k over m, that's the momentum. P over m, that's the classical velocity. So this is v naught t, the velocity associated with that momentum. So this is good. We've done the right job of setting up our wave packet. We built a Gaussian that was far away, that was moving in with a fixed velocity towards the barrier. And now we want to know what happens after it collides off the barrier. Cool? So what we really want to ask is, at late times, what does the wave function look like? Well, at late times, the position of this, so again, we're focusing on the first term, the position of this wave packet at late times at positive t is positive. And when it's positive, then this theta function kills its contribution to the overall wave function, right? This theta is now theta minus a positive number, and this Gaussian is gone. What is it replaced by? Well, these two terms aren't necessarily zero. In particular, this one is moving to the left, so x is, as time goes forward, x is moving further and further to the left. And so this theta function starts turning on. And similarly, as x goes positive, this theta function starts turning on as well. Let's focus on this third term, the transmitted term. So let's focus on this third term. So, in particular, that term looks like integral dk over 2 pi f times the transmission amplitude times e to the I kx minus omega t. Okay, and there's an overall theta of x outside. But for late times, where the center of the wave packet for the transmitted wave packet should be positive, this theta is just going to be 1, so we can safely ignore it. It's just saying we're far off to the right. And now I want to do one last thing. This was an overall envelope. This t was our scattering amplitude, and I want to write it in the following form. I want to write it as root t e to the minus I phi, where phi is a k. So what this is saying is that indeed, as was pointed out earlier, the norm squared of this coefficient t is the transmission probability, but it has a phase. And what I want to know is, what does this phase mean? What information is contained in this phase? And that's what we're about to find. So let's put that in. Here we have root t and minus phi. Okay, where omega and phi are both functions of k, because the transmission amplitudes depend on the momentum, or the energy. Okay. And now I again want to know, how does this wave packet move? If I look at this wave packet, how does it move en masse? How does, as a group of waves, how does this wave packet move? In particular, with what velocity? So I'll do, again, make an argument by stationary phase. I'll look at a point of phase equals 0 and ask how it moves over time. And the point of stationary phase...
So I'm just going to rewrite this the way he has. Yeah. dk over root 2 pi f... What is this k? fk...
phase is again given by ddk of the phase kx minus omega kt minus 5k is equal to 0, evaluated at k0, which is where our envelope is sharply peaked. So this expression is equal to, this is again x minus d omega dk, that's the classical velocity, v naught t, minus d phi dk. But just as a note, d phi dk is equal to d omega dk d phi d omega. But this is equal.
Oh boy. All right. D phi dk.
This is just the chain rule. D omega dk, that's the classical velocity. D omega, or d phi d omega, that's d phi dE times h bar. I just multiplied by h bar on the top and bottom. So this is equal to x minus v naught t plus h bar d phi dE. So first off, let's just make sure that the units make sense. That's a length. That's a velocity, so this had better have units of time. Time, that's good. So h bar times d phase over dE. Well, phase is dimensionless. Energy is units of energy. H is energy times time. So this dimensionally works out. So this is 0. So the claim is that the point of stationary phase has this derivative equal to 0. So setting this equal to 0 tells us that the peak of the wave function moves according to this equation. And so now, so this is really satisfying. This should be really satisfying for a couple of reasons. First off, it tells you that the peak of the transmitted wave packet, not just a plane wave, the peak of the actual wave packet, well localized, moves with overall velocity v naught, the constant velocity that we started with. And that's good. If it was moving with some other velocity, we would have lost energy somehow. That would be not so sensible. So this wave packet is moving with an overall velocity v naught. However, it doesn't move it doesn't move along just as the original wave packet's peak had. It moves as if shifted in time. Okay? So the phase, and more to the point, the gradient of the phase with respect to energy, the rate of change with energy of the phase times h bar, is giving us a phase a shift in the time of where the wave packet is. So what does that mean? So let's be precise about this. So let's interpret this. Here's the interpretation I want to give you. So in the absence, so consider classically this. Classically, we have an object with some energy, and it comes along, it rolls along, and it finds a barrier or a potential well. And what happens when it gets into the potential well? It speeds up, right? Because it's got a lot more energy relative to the potential. So it goes much faster in here, and it gets to the other side and it slows down again. So if I had taken a particle with velocity, so let's call this position 0, and let's say it gets to this wall at time 0, so it's moving with x is equal to v naught t. If there had been no barrier there, then at subsequent times it would get out here in a time x, that distance over v naught, right? However, imagine this well was extraordinarily deep. If this well were extraordinarily deep, what would happen? Well, basically in here its velocity is arbitrarily large, and it would just immediately jump across this well, yeah? So its velocity, so this would be a perfectly good description of the motion before it gets to the well, but after it leaves the well, the position is going to be v naught t plus, well, what's the time shift? The time shift is the time that we didn't need to cross this gap. And how much would that time have been? That time would have been, well, it's the distance divided by the velocity, right? So that's the time we didn't need. So t plus, it moves as if it's at a later time, t plus L over v naught. Cool? So if we had a really deep well and we watch a particle move, we would watch it move x naught, x is v naught t, v naught t, v naught t, v naught t plus L over v, v naught t plus L over v, okay? So it's the time that we made up by being deep in the well. So there's a classical picture because it goes faster inside. So comparing these, here we've done a calculation of the time shift due to the quantum particle quantum mechanically transiting the potential well. Yeah? So let's compare these. The classical prediction, this says the classical prediction is the time it took, delta t, classical, is equal to L over V naught. And the question is this the same? So one way to phrase this question is this the same as h bar d phi dE evaluated at k naught. Okay. And from our results last time, for the amplitude c over a, we get that phi is equal to, which is just the minus the argument or the phase of c over a, or of the transmission coefficient, transmission amplitude little t. Phi turns out to be equal to k2l minus arctan of k1 squared plus k2 squared over 2 k1 k2 tan of k2l. Okay, I look at this and it doesn't tell me all that much. It's a little bit bewildering. So let's unpack this. What we really want to know is this close to the classical result? Okay. So here's a quick way to check. We know this expression is going to simplify near resonance where the sign vanishes. So let's look, just for simplicity, near the resonance. And in particular, let's look near the resonance K2L is equal to n pi. Then it turns out that a quick calculation gives you that h bar d phi dE, that value of the energy, goes as L over 2 V naught times 1 plus the energy over the depth of the well, V naught. Now remember, the classical approximation was L over V naught. We just did this very quickly. We did it assuming an arbitrarily deep well. So V naught is arbitrarily larger in magnitude than E, so this term is negligible. So where we should compare that very simple naive classical result is here, L over 2 V naught. And what we see is that the quantum mechanical result gives a time shift which is down by a factor of 2. Okay? So what's going on? Well, apparently the things slow down inside. The time that it took us to cross was greater than you would have naively guessed by making it arbitrarily deep. And we can make that a little more sharp by plotting as a function of E over V naught the actual phase shift. So the classical prediction, if you do a better job than saying it's infinitely deep, the classical prediction looks something like this. Okay. And this is for delta t, the time shift, classical. When you look at the correct quantum mechanical result, here's what you find. Oops. Where the difference is a factor of 2. 1/2 a height down, and again, 1/2 a height down. So this is that factor of 2 downstairs. So the wave packet goes actually a little bit faster than the classical prediction would guess, except near resonance. And these are at the resonant values of the momentum. At the resonant values of the momentum, it takes much longer to get across. Instead of going a little bit faster than the classical result, it goes a factor of 2 slower than the classical result. And so now I ask you the question, why is it going more slowly? Why does it spend so much more time inside the well, quantum mechanically, than it would have classically?
Bounce around.
Why is the particle effectively taking so much longer to transit the well near resonance? Yeah, exactly. So the classical particle just goes across. The quantum mechanical particle has a superposition of contributions to its amplitude where it transits, transit, bounce, bounce, transit, transit, bounce, 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 transit. And now you can ask, how much time was spent by each of those imaginary particles imaginarily moving across? And if you're careful about how you set up that question, you can recover this factor of 2, which is kind of beautiful. But the important thing here is when you're hitting resonance, the multiple scattering processes are important. They're not canceling out. They're not at random phase. They're not interfering circuitally with each other. They're interfering constructively. And you get perfect transmission precisely because of the constructive interference of an infinite number of contributions to the quantum mechanical amplitude. Okay? And this is, again, we're seeing the same thing in this annoying slowdown. And this tells us another thing, though, which is that the phase, the scattering phase, the phase in the transmission amplitude, contains an awful lot of the physics of the system. It's telling us about how long it takes for the wave packet to transit across the potential effectively. Yeah. Sorry, the vertical axis here is the time that it takes, the shift in the time due to the fact that it went across this well and went a little bit faster than some. Okay, so empirically what it means is when you get out very far away and you watch the velocity, the motion of the wave packet, and you ask how long has it been since it got to the barrier in the first place, it took less time than you would have guessed by knowing that its velocity is v naught. And the amount of time less is this much time. That answer your question? Good. Yeah?
Why is each of the amplitudes 1/2? Why is the first one it bounces around twice?
So the classical amplitude is, so when we compare the classical amplitude and the limit that v naught goes to infinity, so the comparison is just a factor of 2. Okay, it's more complicated out here, and I guess it's in the limit that v naught is large. This is exactly 1/2. Well, the resonances are leading to this extra factor of 1/2. And so as you, I have to say I don't remember exactly whether as you include the subleading terms of 1/v naught, whether it stays 1/2 or whether it doesn't. But in the limit that v naught is large, it remains either close to 1/2 or exactly 1/2. I just don't remember exactly. The important thing is that there's a sharp dip. It takes much longer to transit, and so you get less bonus time, as it were. You've gained less time in the quantum mechanical model than. And when you do the experiment, you get the quantum result. So that's the crucial point. Other questions? Okay. So the phase contains an awful lot of the physics. So I want to generalize this whole story in a very particular way. And this way of reorganizing the scattering in 1D. So what we're doing right now is we're studying scattering problems in 1 dimension. But we live in 3 dimensions. The story's going to be more complicated in 3 dimensions. It's going to be more complicated in 2 dimensions. The basic ideas are all the same. It's just the details are going to be different. And one thing that turns out to be very useful in organizing scattering, both in 1 dimension and in 3 dimensions, is something called the scattering matrix. I'm going to talk about that now. In 3 dimensions, it's essential. But even in 1 dimension, where it's usually not used, it's a very powerful way to organize our knowledge of the system as encoded by the scattering data. So here's the basic idea. As we discussed before, what we really want to do in the ideal world is take some unknown potential in some bounded region, and outside we have the potential is constant, modulo my bad artistic skills. So potential is constant out here. And the potential could be some horrible thing in here that we don't happen to know, and we want to read off of the scattering process. We want to be able to deduce something about the potential. So, for example, we can deduce the energy of our step, or we can deduce the energy by looking. So good. We can deduce the energy by looking at the barriers, and we can disentangle the position of the energy and the width, the depth and the width, by looking at the phase shift. By looking at the time delay. So we can deduce all the parameters of our potential by looking at the resonance points and phase shift. I want to do this more generally for a general potential. And to set that up, we need to be a bit more general than we've been. Okay. So in general, if we solve this potential, as we talked about before, we have A and D, equals B, x minus x here, and out here we have C e to the ikx and D e to the minus x. And I'm not going to ask what happens inside. Now we can discuss 2 kinds of scattering experiments. We can send things in from the left, in which case A is non-zero, and then things can either transmit or reflect, but nothing's going to come in from infinity, so D is 0. Or we can do the same in reverse, send things in from here, and that corresponds to A is 0, nothing coming in this way, but D non-zero. And more generally, we can ask the following question. Look, suppose I send some amount of stuff in from the left, and I send some amount of stuff in from the right D, then that will tell me how much stuff will be going out to the right and how much stuff will be going out to the left. Yeah? If you tell me how much is coming in, I will tell you how much is coming out. BC. So if you could solve this problem, The answer is just some relation, some pair of linear relations between these, and we can write this as a matrix, which I will call S11, S12, S21, S22. Okay. What this matrix is doing is it takes the amplitude you're sending in from the left or right and tells you the amplitude coming out to the left or to the right. Yes.
How do we know this relation is linear?
If you double the amount of stuff coming in, then you must double the amount of stuff going out, or probability is not conserved. Also, we've derived these relations. You know how the relations work. The relations work by satisfying a series of linear equations between the various coefficients such that you have continuity and differentiability at all the matching points. But the crucial thing of linearity is probability is conserved and time evolution is linear. So, other questions? Okay, so this is just some stupid matrix, and we call it, not surprisingly, the S matrix in all of its majesty. The basic idea is this: for scattering problems, if someone tells you the S matrix, and in particular, if someone tells you how all the coefficients of the S matrix vary with energy, then you've completely solved any scattering problem. You tell me what A and D are, great, I'll tell you exactly what B and C are, mode by mode, and I can do this for a superposition. So this allows you to completely solve any scattering problem in quantum mechanics once you know it. So it suffices to know S to solve all scattering problems. So I want to now spend just a little bit of time thinking about what properties the S matrix and its components must satisfy. What properties must the S matrix satisfy in order to, jive well with the rest of the rules of quantum mechanics? And I'm not going to study any particular system. I just want to ask general questions. So the first thing that must be true is that stuff doesn't disappear. Disapparate is probably the appropriate. Stuff doesn't leak out of the world. So whatever means is norm of A squared plus norm of D squared, which is the probability density in and probability density out, must be equal to B squared plus C squared. Okay. Everyone agree with that? Why can't stuff stay in potential? That's a good. So it's a stationary state. So if we're looking at fixed energy ideal states, we know that we're in a stationary state. So whatever the amplitude going into the middle is, it must also be coming out of the middle, right? So there's another way to say this, which is that let's think about it not in terms of individual energy eigenstates. Let's think about it in terms of wave packets. So if we take a wave packet of stuff and we send in that wave packet, it has some momentum, right? This is going to get delicate technical. Let me just stick with the first statement, which is that if stuff is going in, then it has to also be coming out by the fact that this is an energy eigenstate. The overall probability distribution is not changing in time. So if stuff went in and it didn't come out, that would mean the same there. That would mean the probability density is changing in time. That's not what happens in an energy eigenstate. Probability distribution is time dependent. Everyone go that? Okay. So, good. So let's think though about what this is. I can write this in the following nice way. I can write this as A complex conjugate, D complex conjugate, AD. And on the right hand side, this is equal to B complex conjugate, C complex conjugate. DC. I've done nothing other than write this out in some suggested form. But B and C are equal to the S matrix. So BC is the S matrix times A, and B complex conjugate, C complex conjugate is the transpose complex conjugate. So this is equal to A complex conjugate, D complex conjugate. S transpose complex conjugate, also known as adjoint, and this is S on AD. Yeah? But this has to be equal to this for any A and D. So what must be true of S dagger S as a matrix? It's got to be the identity as a matrix in order for this to be true for all A and D. Ah, that's cool. Stuff doesn't disappear. S is a unitary matrix. So S is a unitary matrix. Its inverse is its adjunct. And you'll prove this in a little more elegance. You'll study this in a little more detail. On the problem set, you showed the definition of unitary. You studied the definition of unitary in the last problem set. Okay, so that's the first thing about S, and it turns out to be completely general. Anytime, whether you're in 1 dimension or 2 dimension or 3, if you send stuff in, it should not get stuck. It should come out. And when it does come out, the statement that comes out for energy eigenstates is the statement that S is a unitary matrix. Questions on that? Okay. So, a consequence of that is that the eigenvalues of S are phases, pure phases. So I can write S, I'll write them as S1 is equal to ETI phi 1, and S2 is equal to ETI phi 2. So the statement that S is a unitary matrix leads to constraints on the coefficients. Okay, and you're going to derive these on your problem set. I'm just going to list them now. So the first is that the magnitude of S1 is equal to the magnitude of S22. The magnitude of S12 is equal to the magnitude of S21. Oops. Good. And more importantly, S12 squared plus S11 squared is equal to 1. Finally, S11, S12 complex conjugate plus S. To 1, S22 complex conjugate is equal to 0. So, what do these mean? What are these conditions telling us? What are these? So they're telling us, of course, they're consequences of conservation of probability, but they have another meaning. And to get that other meaning, let's look at the definition of the transmission amplitudes. So in particular, consider the case that we send stuff in from the left and nothing in from the right. So that corresponds to D equals 0. So when D equals 0, what does this tell us? It tells us that B is equal to and A equals 1 for location. So B is equal to, well, D is equal to 0, so it's just S11 A. So B over A is S1.
All right, B would be S11A. But we know D is 0, so.
1. And similarly, C over A is S21.
That would be over here.
But C over A is the thing that we've been calling the transmission amplitude, little t. And this is the reflection amplitude, little r. So this is the reflection amplitude if we send in stuff and it bounces off or reflects to the left. And this is the transmission amplitude for transmitting to the right. Ever go with that? And by the same token, so this is reflection to the left, this is transmission to the right. By the same token, this is going to be transmission to the left and reflection to the right. So now let's look at these conditions. S11 is reflection, this is going to be reflection. This says that the reflection to the left is equal to the reflection to the right. In magnitude. before, what we saw was for the simple step, the reflection was equal to the reflection. The reflection amplitude was equal from left or right. Not just the magnitude, but the actual value was equal from left and right. It was a little bit cheap because they were real. And we saw that that was a consequence of just being the step. We didn't know anything more about it. But now we see that on general grounds, on conservation or probability grounds, the magnitude of the reflection to the left and to the right for any potential.
This means.
And similarly, the magnitude of the transmission from the left and the transmission to the right have got to be equal. All of the things being, if you're sending it to the left and then transmitting to the left, or sending it from the right and transmitting to the right. And what does this one tell us? Well, S12 and S11, that tells us that t squared, little t squared, which is total probability to transmit, plus little r squared, norm squared is the total probability to reflect, is equal to 1. We saw this one. Last time too. This was the earlier definition of nothing gets stuck. And this one, you'll study under problem set. It's a little more simple. Okay, questions? Yeah. Yeah, I got SSW. So the way they got SSW energy, first off, this is just a definition of that. S is the matrix that for any energy relates A and B in going amplitudes, the outgoing amplitude B and C. Just a definition. Meanwhile, I played that stuff doesn't go away, nothing gets stuck, nothing disappears. So the total probability density of stuff going in must be the total probability density of stuff going out. But the probability of stuff going in can be expressed as this row vector times this column vector, and on the out, this row vector times this column vector. And then we use the definition of gas makers. This column vector is equal to S times this row vector. Yeah? BC is equal to S times AD. And when we take the transpose complex conjugate, I get AD transpose complex conjugate, S transpose complex conjugate, but that's the S adjoint. But in order for this to be true for any vectors A and D, it must be that S dagger S is the identity. But that's the definition of a unitary matrix. Cool? Others? Okay. You're going to prove a variety of things on the problem set about the scattering matrix and its coefficients. But I want to show you two properties of it. The first is reasonably tame, and it'll make a little sharper the step result we got earlier, that the reflection in both directions off the step potential was in fact exactly the same. So, where did I put this? Good. So suppose our system is time reversal invariant. So t plus minus t, nothing changes. This would not be true, for example, if we had electric currents in our system, because if we take t minus t, then the current reverses. So if the current shows up in the potential, or if a magnetic field current shows up in the potential energy, then as we change t minus t, we change the direction of current, change the direction of the magnetic field. So in simple systems where we have time reversal invariance, for example, electrostatics, but not, for example, magnetostatics, suppose we have time reversal invariance, then what you've shown on the previous problem set is that psi is a solution. Then psi star, psi complex conjugate, is also a solution. And using these, what you can show, and I'm not going to go through the steps for this. Well, okay, that's easy. So if we do the time reversal, the wave function, looking on the left or on the right, so comparing these guys, so what changes? Well, in time reversal, we get a solution. So given this solution, we have another solution. A star equal minus ikx, b star equal plus ikx, so minus star plus. Okay, so we can run exactly the same game now with this amplitude. And when you put these conditions, when you put the conditions together, which you'll do on the problem set, so another way to say this is the same solution k minus k, and with a and b replaced by their complex conjugates, and c and d replaced by each other's complex conjugates. Then this implies that it must be true that a and d, which are now the outgoing guys because we've time reversed, is equal to s, and I'll write this out explicitly, s11, s12, s21, s22, b star, and c star. And so these together give you that. Should have done this over here. Therefore, S complex conjugate S is equal to 1. Okay. So if S complex conjugate S is equal to 1, then S inverse is equal to S transpose. Just putting this on the right. So S transpose is equal to S inverse is equal to S adjoint, because S is also unitary. So time reversal invariance implies, for example, that S is equal to that S dagger is equal to S star, S is equal to S transpose. Time reversal. This is what I wanted right here. So we did this, that S is equal to S transpose. And in particular, this tells us that S21 is equal to S12. The off-diagonal terms are equal. Not just in magnitude, which was ensured by unitarity, but if in addition to being a unitary system, which of course it should be, if in addition it's time reversal invariant, then we see that the off-diagonal terms are equal not just in magnitude, but also in phase. And as you know, the phase is important. The phase contains physics. It tells you about time delays and shifts in the scattering process. So the phases are the same. That statement is not a trivial one. It contains physics. So when the system is time reversal invariant, the phases as well as the amplitudes are the same. It'll provide a series of related conditions or consequences for the S matrix some various properties of the system, for example, parity, if you have symmetric potential. But now I wanted, in the last few minutes, I just want to tell you a really lovely thing. So it should be pretty clear at this point that all the information about scattering is contained in the S matrix and its dependence on the energy. If you know what the incident amplitudes are, you know what the outgoing amplitudes are. And that's cool because you can measure this, right? You can take a potential, you can literally just send in a beam of particles, and you can ask how likely are they to get out, and more importantly, if I build a wave packet, on average, what's the time delay or acceleration of the transmitted wave packet? That way I can measure the phase as well. I can measure both the transmission probabilities and the phases, at least the gradient of the phases of energy. Hold on. Go ahead.
Is there a special condition if we can pose it to see the resonance?
Excellent question. Hold on to your question for a second. Yeah. So there's an enormous amount of the physics of scattering contained in the S matrix. And you can measure the S matrix. And you can measure its dependence on the energy. You can measure the coefficients S12 and S22, the phases and their amplitudes, as a function of energy. And you can plot them. And here's what I want to convince you of. If you plot those and look at how the functions behave as functions of energy, and ask how do those functions extend to negative energy, by just drawing a line, continuing lines, you can derive the energy of any bound states in the system too. Knowledge of the scattering is enough to determine the bound state energies of a system. And let me show you that. And this is one of the closest. So here's how this works. We have, from the definition of the S matrix, that VC is equal to the S matrix on AD, right? Where the wave function, let me just put this back in the original form, is CD, AB, e to the IKX, e to the minus IKX, and e to the plus IKX, e to the minus IKX. Yeah? So that's the definition of the S matrix. The S matrix at a given energy E is this relation, the coefficient relation matrix between the ingoing and outgoing, or more than point A and D. And in all of this, I've assumed that the energy was positive, that the K1 and K2 are positive and real. But now let's ask the question, what would have happened if in the whole process I had taken the energy less than 0. So if the energy was less than 0, instead of K would be replaced by I alpha. Let's think about what that does. If K is I alpha, this is e to the IK is minus alpha, and minus IK is plus alpha, Similarly, IK times I, it's going to be minus alpha, and this gives me plus alpha. Yeah? So as equations are the same equations with K replaced by I alpha. Yeah? And now, what must be true for this state, for these states to be normalizable? What must be true, for example, of A? A must be 0 because at minus infinity is divergent, it's not normalizable. So in order to be a bound state, in order to have a physical state, A must be 0. What about D? Same reason, it's got to be 0 at positive infinity. These guys are convergent, so C and D can be non-zero. So now here's my question. Can I scatter a state from A, B? We know that these relations must be true because all these relations are encoding. All these relations are encoding is how a solution theorem matches to a solution theorem through a potential in between, with continuity of the derivative, and anything else that's true of that potential inside. All that S is doing from that point of view is telling me how these coefficients match onto these coefficients. Yes? Now, what for a bound state? So if we have E less than 0, what must be true? We must be true that AB is equal to 0. And particular 0, 0. Right? So what are B and C? Oh, well, a matrix times 0 is equal to, unless the matrix itself is divergent. And then you have to be more careful. But let's be naive for a moment. If A is 0, 0, then in order for B and C to be non-zero, S must have a pole. S must go like 1 over 0. S must... converge to some special value of the energy. Okay, well that's easy. That tells you that if you look at any particular coefficient in S, any of the matrix elements of S, the numerator can be whatever you want, some finite number, but the denominator had better be 0. So let's look at the denominator. If I compute S21, actually, let me do this over here. Let's compute. No, it's all filled. Damn. Let's get over here. So if I look at S21 for the barrier, or for the potential well, scattering off the potential well, if we look at the beginning of today's lecture, this guy. And now I'm going to look at S21, one of the coefficients of this guy, also known as the scattering amplitude T for the well. This is equal to, and it's a god-awful expression, 2k1, k2, e to the I, k2l, over 2k1, k2, cos of k prime l, minus I, k squared, plus k1 squared plus k2 squared, times sine of k2l. Okay, this is some horrible thing. But now I ask the condition, look, when does... have a pole? For what values of the energy does this, when the energy is continued to be negative, for what values does this have a pole, or does the denominator have a 0? And the answer is, if you take this and you massage the equation, this is equal to 0 a little bit, you get the following expression. K2L upon 2, tangent of K2L upon 2 is equal to K1L upon 2. This is the condition for the bound state energies of the square well. And we've computed it using knowledge only of the scattering states. If you took particles and a square well and rolled the particles across the square well potential and measured as a function of energy the scattering amplitude, the transmission amplitude, in particular S21, an element of the S matrix, and you plotted it as a function of energy, and then you approximated that by a function of energy that satisfies the basic properties of unitarity, what you would find is that when you then extend that function in Mathematica to minus a particular value of the energy, the denominator diverges. At that energy, you know that there will be a bound state. And so from scattering, you've determined the existence of a bound state. And this is how we find an awful lot of the particles that we actually deduce must exist in the real world. We'll pick up next time.
Okay, so this was a tricky class. The S matrix stuff seems to make sense. I just want to go through and make some points about some stuff that I didn't quite understand. So this whole stationary phase thing. So let's see if I can just kind of recap what was discussed. So this whole section here, I'm just going to write it with pen because I think it's sometimes useful to just jot down what things. I'm just going to put like a, so I think I understood this because this is just the, yeah, this makes sense. So the question is, what is happening from basically here on? And let's see if we can put the timestamp for that. And then it was up until about the, so I'm going to just put a note here. And then like where was this happening? So let me just see if I can find this in the video and just make a timestamp so that I can watch from that section. So let's go a little bit before we're here. I think that's this here. Okay, we did this here. So let's just say this is about 36. I say it's around 36 minutes. And then when did we start doing scattering matrix? That was, I think, right here. So let's say it's about 57. So I'm just going to make a little notes here. Lecture 14 notes. I didn't understand analysis between what was discussed. Well, Okay, so I'm not going to stop. I think I will continue forward. This is probably going to come up in the problem set, but I've marked off the exact minutes. It looks like there's about 21 minutes there. So I may go through that 21 minutes again. I may try to find something in the book here to kind of analyze it. Let me open lecture 15 here.
Content is provided under a Creative Commons license. Your support will help.
I'm just going to quickly take 1 second just to fill up my water, take a little breath and break, and I will be back with lecture 15. All right, I'm back. I don't have any idea whether anyone's watching, but let's get into lecture 15. So we're making good progress. Overall, I think I'm going to be able to meet my lecture watching deadlines, and we're going to have a good 2 weeks after to really drill down on things. So I think there's enough time to get through this class, but we got to keep up the pace and make sure that there is some section here that I didn't understand. I don't think it's going to come back again, so it's going to be maybe like lecture 8 and 9, although I bounded when it happens, so I don't have to be searching through and trying to figure out when whatever is happening is happening.
Help MIT OpenCourseWare continue to offer for free. To make a donation or to view it.
Hi, everyone. We're getting forward.
I'm finding watching it 1.5 times and pausing it a little better than just 1x, because very often he's talking slowly about something that isn't, not straining my understanding. So I'm only going to slow it down when there's a lot of math and I'm pausing it too frequently.
This semester, things are starting to cohere and come together. We have one more midterm exam. So there's an exam next Thursday, the 18th. Okay. There will be a problem set due. It will be posted later today, and it will be due next week on Tuesday, as usual. Of course, next week on Tuesday is a holiday, technically, so we'll actually make the due date be on Wednesday. So on Wednesday, you should think of this problem set as part of the review for the exam. Material that is covered today and on Thursday will be fair game for the exam. Okay. So the format of the exam is going to be much more canonical. It's going to be a series of short answer plus a series of computations. They'll be roughly speaking at the level of the problem sets, and practice exam will be posted in the next couple of days. Okay. And the classic exam. The practice exam is going to be of the same general intellectual difficulty, but it's going to be considerably longer than the actual exam. So as a check for yourself, here's what I recommend. I recommend sitting down and getting yourself an hour and a half or 2 hours with the practice exam and see how that goes. Okay. Try to give yourself the time to check. And here's one of the things that there's a very strong correlation between having nailed the problem sets and worked through all the practice exams and just done a lot of problems and doing well in the exams. We're confident. The only way to study that these things is to do a lot of problems. So on Stellar, for example, are a bunch of previous problem sets and previous exams and practice exams from previous years. I would encourage you to look at those, also on the CW, and use those as practice. Okay, any practical questions before we get into this? Yeah. Well, this is a cumulative topic, so the question is, does it cover everything or just the last couple of weeks? And it's a cumulative topic, so the entire semester is necessary in order to answer the problems. Other questions? Okay, anything else? So, quick couple of review questions before we launch into the main material of today. These are going to turn out to be useful reminders later on in today's lecture. So, first, suppose I tell you I have a system with energy operator E, which has an operator A, such that the commutator E with A is, let's say, plus H bar A. Okay? What does that tell you about the spectrum of the energy operator?
Discrete.
It's a ladder, exactly. So this tells you that the spectrum of E, or the energy eigenvalues En, are evenly spaced. And we need, sorry, I need a dimensional constant here, omega. Evenly spaced by H bar omega. And more precisely, that given a state phi E, we can act on it with the operator A to give us a new state, phi, which is also an energy eigenstate, with energy E plus H bar omega. Right? So anytime you see that commutation relation, you know this fact to be true. Second statement, suppose I have an operator B, which commutes with the energy operator. Okay, so that the commutator vanishes. What does that tell you about the system?
Means that there's both simultaneously measurable.
Excellent. So one consequence is that there exist simultaneous eigenfunctions, phi sub E, comma B, which are simultaneous eigenfunctions of both E and B. What else does it tell you? Well, notice the following. Notice that if we took this commutation relation and set omega to 0, we get this commutation relation. So this commutation relation is of the form of this commutation relation with omega equals 0. So what does that tell you about the states? About the energy eigenvalues?
Continuous.
What happens if I take a state, phi sub E, and I act on it with B? What do I get? What can you say about this function? Well, what is its eigenvalue under E? It's E. It's the same thing because they commute. You can pull the E through, multiply, you get a constant E, you pull it back out. This is still an eigenfunction of phi, or of the energy operator, with the same eigenvalue. But is it necessarily the same eigenfunction? No, because B may act on phi and just give you a different state. So this is some eigenfunction with the same energy, but it may be a different eigenfunction. Okay. So let's think of an example of this. An example of this is consider a free particle. Okay. In the case of a free particle, we have E is equal to P squared upon 2m. And as a consequence, E and P commute. Everyone agree with that? Everyone happy with that too? They commute. So plus 0 if you will. And here, what I wanted to say is when you have an operator that commutes with the energy, then there can be multiple states with the same energy, which are different states, right? Different states entirely. So for example, in this case, what are the energy eigenfunctions? Well, e to the ITX. And this has energy h bar squared k squared upon 2m. But there's another state, which is a different state, which has the same energy, e to minus ITX. Okay? So, when you have an operator that commutes with the energy operator, you can have simultaneous eigenfunctions, and you can also have multiple eigenfunctions that have the same energy eigenvalue. For example, this. Well, that. Now, just to be clear, that actually the commuting that matters. Imagine we took out the free particle, but the harmonic oscillator. E is p squared upon 2m plus m omega squared upon 2 x squared. Is it true that E, I'll call this harmonic oscillator, does E harmonic oscillator commute with P? No, you're going to get a term that's m omega squared x from the commutative. The potential is not translationally invariant. It does not commute with momentum. So this is not equal to 0. So that suggests that this degeneracy, two states having the same energy, should not be present. And indeed, are the states degenerate for the harmonic oscillator? No. Okay. No degeneracy. Yeah. Yes. What does it mean for the eigenfunctions to be complete? What that means is that they form a basis. So. Yeah, no one told you that the basis had to be degenerate. And in particular, that's an excellent. So the question here is, wait a minute. I thought a basis had to be a complete set. If you had an energy operator, and you constructed the energy eigenfunctions, this is a very good question, thank you. If I have the energy operator, and I construct its energy eigenfunctions, then those energy eigenfunctions form a complete basis for any arbitrary function. Any function can be expanded in, right? So for example, for the free particle, the energy eigenfunctions are e to the ITX and the momentum eigenfunctions for any value k. But wait, how can there be multiple states with the same energy? Isn't that double counting or something? And the important thing is, those guys have the same energy, but they have different momentum. They're different states. One has momentum h bar k, one has momentum minus h bar k. And you know that that has to be true because the Fourier theorem tells you, in order to form a complete basis, you need all of them, all possible values of k. Okay? So there's no problem with being a complete basis and having states have the same energy eigenvalue. Okay? It's a good question. Other questions? Yeah.
So if we have potential that really like bound states, so we're going to have the computation have to be.
Yeah, exactly. Excellent. So the observation is this. Look, imagine I have a potential that's not trivial. It's not 0. Okay? Will you have momentum constant? Will the momentum give you the energy operator? No, because it's got potential that's, going to be acted upon by P, so later return. But more precisely, if I have a system with bound states, if I have a system with bound states, I have to have a potential, right? And then I can't have P commuting with the energy operator, which means I can't have degeneracies. Right? So indeed, if you have boundaries, you cannot have degeneracies. That's exactly right. Yeah. Excellent. So we're going to come back to higher dimensions later. So the question predicts what's going to happen in the rest of the lecture. What we're going to do in just a minute is we're going to start working in 3 dimensions for the first time. We're going to leave 1D behind. We're going to take our tripped out tricycle and replace it with the Yamaha. Okay. As you'll see, it has the same basic physics driving its itself. It's the same dynamics. But I want to emphasize a couple things that are going to show up. So the question is, isn't this story different in 3 dimensions? And we shall see exactly what happens in higher dimensions. We'll work in 2 dimensions. We'll work in 3 dimensions. We'll work in more. Doesn't really matter how many dimensions we work in. You'll see. Okay, third thing. This comes from, you studied this in some detail in your problem set. Suppose I have an energy operator that commutes with a unitary operator, U. Okay, so it commutes to 0. And U is unitary, so U dagger U is 1, is the identity. So what does this tell you? Well, first off, from these guys, it tells us that we can have, let's take this one, simultaneous eigenfunctions. It also tells us, too, that if we take our state phi and we act on it with U, this could give us a new state, phi tilde sub E, which will necessarily have the same energy eigenvalue because U and E commute, but it may be a different state. We'll come to this in more detail later. But the third thing I want to emphasize is this tells us, look, we have a unitary operator. We can always write the unitary operator as e to the I, a Hermitian operator. So what is the meaning of this Hermitian operator? What is this guy? So in your problem set, you looked at what unitary operators are. And in the problem set is discussed in some detail, there's a relationship between a unitary transformation or unitary operator and a symmetry. A symmetry is when you take your system and you do something to it, like a rotation or a translation, and it's a symmetry if it doesn't change anything, if the energy remains invariant. So if the energy doesn't change under this transformation, we call that a symmetry. In particular, and we also showed that symmetries or translations are generated by unitary operators. For example, my favorite examples are the translate by L operator, which is unitary, and also e to the minus I, or e to the minus dx L, and the boost by Q operator, which similarly is e to the minus Q dp, and the time translation operator, U sub t, which is equal to e to the minus I t over h bar energy operator. Okay, so these are transformation operators. These are symmetry operators, which translate u by L, boost your speed u up by the momentum q, evolve you forward in time t, and they can all be expressed as e to the unitary operator. So this in particular is L I over h bar p, and this is similarly x. And earlier we understood the role of momentum having to do with translations in the following way. There's a beautiful theorem about this. If you take a system and it's translation invariant, the classical statement of another theorem is that there's a conserved quantity associated with that translation. That conserved quantity is the momentum. And quantum mechanically, the generator of that transformation, the Hermitian operator that goes upstairs in the unitary, is the operator associated to that conserved quantity, associated with that observable. You have translations, there's a conserved quantity which is momentum, and the thing that generates translations, the operator that generates translations, is the operator representing momentum. So each of these is going to come up later in today, and I just wanted to flag them down for the moment. Okay, questions before we move on? Yeah?
So do you think that every unitary operator in this class is easy to average?
Okay, I should be a little bit careful. Yes, that's right.
So I think so if I take a logical size and I take that, you have to figure out what it is, but you can take a log.
The more precise statement is that any one parameter family of unitary operators can be expressed in that form. So, and then you can take the derivative, and that's the theory of Lee algebras, which so to make that, so let me make a very specific statement, which is that one parameter families of unitary translations of translations by L with unitary L can be expressed in that form. And that's a very general statement. Okay, so with all that as prelude, let's go back to 3D. So in 3D, the energy operator, so what's going to change? Well, now instead of just having position and its momentum, we now also have a piece of x. We also have a y coordinate and we have a z coordinate, and each of them has its momentum, piece of z and piece of y. Okay. And here's just a quick practical question. We know that x with px is equal to I bar. Okay. And we know that, so what do you expect to be true of x with y? Y. What does this equation tell you? What is its physical content? Well, that they don't compute. What does that tell you physically? Yes.
That there's an uncertainty principle connecting the two.
Excellent. So that's one statement. So the consequence of this is that there's an uncertainty principle delta x tells px must be greater than or equal to 8 upon 2. What's another way of saying this?
I guess this is 0.
Do there exist simultaneous eigenfunctions of x and p? No. No simultaneous eigenfunctions. Okay, so you can't have a definite value of x and a definite value of p simultaneously. There's no such state. It's not that you can know, it's that there's no such state. Do you expect to be able to know the position in x and the position in y simultaneously? Sure.
Yes.
Okay, so this turns out to be 0, and in some sense you can take that as a definition of quantum mechanics. It's 1 to be 0. And similarly, px and py compute. The momenta are independent. However, py and y should be equal to minus I h bar. Good, exactly. So the commutators work out exactly as you'd manually expect. Every pair of position and its momentum are commute canonically to I h bar. And every pair of coordinates commute to 0. Every pair of momenta commute to 0. Cool? Okay, so what kind of systems are we going to be interested in? Well, we're going to be interested in systems where the energy operator is equal to now p vector hat squared upon 2m plus u of x and y and z hat hat. You can see why dropping the hats, it becomes almost necessary. Okay. So in this language, we can write the Schrödinger equation. This is just a direct extension of the one equation, I h bar dt of psi. Now our wave function is a function of x and y and z. There's some finite probability density to find particle at some position. That position is labeled by the 3 coordinates. Is equal to, n of t is equal to, well, I'm actually going to write this in a slightly different form. This is going to be easier if I use vector notation. So I'm going to write this as psi of r and t, where r denotes the position vector, is equal to, well, the energy operator acting on it, and p is just equal to minus I h bar, the gradient. So this is minus I h bar squared, or minus h bar squared upon 2m, gradient squared, plus u of x, or now u of r, psi of r and t. Quick question, what are the units, or what are the dimensions of psi of r in 3D?
So this is going to be we want a norm square to give us the same thing. But now it's going to be over 3 dimensions, so it's going to be square root of length cubed.
Yeah, 1 over length to the root 3 halves. And the reason is, this norm squared gives us a probability density, something that when we integrate it over all positions in a region, integral d3x is going to give us a number of probability. So its actual magnitude must be 1 over, or its dimension must be 1 over L to the 3 halves. Just the cube of what it was in 1D. Okay. And as you'll see on the problem set, as we'll do in a couple lectures down the road, it's convenient sometimes to work in Cartesian, but it's also sometimes convenient to work in spherical coordinates. And it does not matter, and here's a really deep statement that goes way beyond quantum mechanics. It does not matter which coordinates you work in. You cannot possibly get a different answer by using different coordinates. So we're going to be ruthless in exploiting coordinates that will simplify our problem throughout the rest of this course. In the notes is a short discussion of the form of the Laplacian, or the gradient squared, in Cartesian, spherical, and cylindrical coordinates. You should feel free to use any coordinate system you want at any point. You just have to be consistent about it. So let's work out a couple of examples. There you go. They apply exactly the same logic that we see over and over in 1D to our 3D problems. So the first example is a free particle in 3D. So before we get started, any questions? Just in general 3D questions. Okay. So this stuff starts off easy. And I'm going to work in Cartesian coordinates. And a fun problem is to repeat this analysis in spherical coordinates, and we'll do that later on. Okay, so free particle in 3D, so what does the energy eigenfunction equation look like? We want to find, the Schrödinger equation has exactly the same structure as before. It's a linear differential equation. So if we find the eigenfunctions of the energy operator, we can use superposition to construct the general solution, right? So exactly as in 1D, I'm going to construct first the energy eigenfunctions, and then use them in superposition to find the general solution to the Schrödinger equation. Okay, so let's construct the energy eigenfunctions. So what does the energy eigenvalue equation look like? Well, E on psi is equal to minus h bar squared upon 2m. And in Cartesian, the Laplacian is derivative with respect to x squared, plus derivative with respect to y squared, plus derivative with respect to z squared. And we have no potential, so this is just psi. So that would be the energy operator acting on it. And value equation is that a constant, the energy E on psi is satisfies this equation. And we write this phi sub E to continue with our notation of phi being the energy eigenfunctions. It of course doesn't matter what I call it, but just for consistency, I'm going to use the letter phi. So this is a very easy equation to solve. We can write it, in particular, it has a lovely property, which is that it's separable. Okay. So separable means the following. It means, look, I just observed that this differential equation can be written as a sum of terms where there's a derivative with respect to only one variable, there's a differential operator with respect to only one variable, and another differential operator with respect to only one variable added together. And when you see that, you can separate. And here's what I mean by separate. I'm going to just construct. I'm not going to say that this is a general solution. I'm just going to try to construct a set of solutions of the following form. Psi e of x, y, and z is equal to psi e. I will call this psi sub x of x times psi phi sub y of y times phi sub z of z. Okay. And if we take this and we plug it in, let's see what we get. This gives us that e on phi e is equal to minus h bar squared upon 2m. Well, the dx squared acting on phi sub e is only going to hit this guy. So I'm going to get phi x prime prime, phi y phi z, plus, for the next term, phi y prime prime, phi x phi z. And for the next term, phi z prime prime, phi x phi y. But now I can do a sneaky thing and divide the entire equation by phi sub e. Phi sub e is phi x phi y phi z. So if I do so, I lose. To phi y phi z, and I divide by phi x. And in this term, when I divide by phi x phi y phi z, I lose the x and z, and I have it left over phi sub y, or phi y. And similarly here, phi sub z upon phi z. Everyone cool with that? Yeah? I don't think so. Minus h bar squared over 2m just hangs out for the ride. Yeah. So when I take the derivatives, I get these guys. Then I have e times the function. Yeah. We could certainly write this as 2 here. That's fine. Okay. So this is the form of the equation we have. And what does this give us? What concept does this give us? Well, note the following. This is a funny system. This is a function of x. This is a function of y, g of y, only, and not of x or z. And this is a function only of z and not of x or y. Yeah? So we have that e, and let's put this as minus 2m over h bar squared, is equal to a function of x plus a function of y plus a function of h. What does this tell you? They're all constant, right? So the important thing is this equation has to be true for every value of x, y, and z. It's a differential equation. It's true everywhere. It's true here, it's true there, it's true at every point. Yeah? So for any value of x, y, and z, this equation must be true. So now imagine I have a particular solution, g and h. I'm going to fix y and z to some particular point. I'm going to look right here. And here that fixes y and z. So these are just some numbers. And suppose we satisfy this equation. Then as I vary x, leaving y and z fixed, what must be true of f of x? It's got to be constant. Exactly. So this tells us that f of x is a constant, i.e. phi x prime prime over phi x is a constant. I'll call it epsilon x. And phi y prime prime over phi y, and this is a function of y, of x, is equal to epsilon y. And actually for, yeah, that's fine. Look, for fun, I'm going to put in a minus. It doesn't matter what I call this coefficient. And similarly for phi z prime prime z over phi z is equal to minus epsilon z. So this tells us that minus 2m upon h bar squared e is equal to minus epsilon x minus epsilon y minus epsilon z. And any solutions of these equations with some constant value of epsilon x, epsilon y, and epsilon z is going to give me a solution of my original energy eigenvalue equation where the value of capital E is equal to this sum. And I can take away the minus signs, make this plus plus. Yeah.
Can epsilon x, epsilon y, and epsilon z
Well, let's check. Let's check. So what are the solutions of this equation? Yeah, so solutions of this equation, phi double prime. So let's write this in a slightly more familiar form. This says that phi prime prime plus epsilon x phi is equal to 0. Okay, but this just tells you that phi is exponentials. Phi is equal to a e to the I kx, kxx, plus b e to the minus I kxx, where h bar squared, where k squared is equal to kx squared is equal to epsilon x. Okay. So this becomes, and similarly for epsilon y and epsilon z, each with their own value of ky and kz, whose square is the epsilon. So what can you say about these epsilons? Well, the epsilons are strictly positive numbers. So that answers your question. So the epsilons have to be positive. Okay, so this equation becomes, though, e is equal to, I'm going to put the h bar squared over 2m back on the other side, h bar squared upon 2m, epsilon x, epsilon y, epsilon z, but those are just kx squared plus ky squared plus kz squared, kx squared plus ky squared plus kz squared. Also known as h bar squared upon 2m, k vector squared, where the wave function, phi sub e, is equal to some overall normalization constant times, for the first function, where did the definition go? Right here. So from here, phi x is the exponential with kx, this is the exponential in y with ky, and then the exponential in z with kz, e to the I, kx times x, plus ky times y, plus kz times z. Right. You write this as e to the I, e to the I. Okay, also known as some normalization constant e to the I, k vector dot r vector. Okay. So the energy, if we have a free particle, the energy eigenfunctions, put in the form, at least we can build energy eigenfunctions of the form, plane waves with some 3D momentum. With energy, E is equal to h bar squared, k squared upon 2m. Just as we saw for the free particle in one dimension. And the actual wave function is nothing but a product of wave functions in 1D. Yeah?
What happened to the minus 9k?
Oh, good. So here I just dropped these guys. So I just picked an example where we just picked the EVX. Right. So that's an excellent question. So I've done something here. In particular, I looked at a special case. And here's an important lesson from the theory of these separable equations, which is that once I separate, so if I have a separable equation, if I have a separable equation, and I find a separated solution, phi e is equal to phi x of x, phi y of y, phi z of z. Not all functions, not all solutions of the equation are of this form. They're not. I had to make that assumption. I said, suppose it's of this form. Right here. So this is an assumption. Okay. However, these form a good basis. By taking suitable linear combinations of them, suitable superpositions, I can build a completely general solution. For example, as was noted, the true solution of this equation, even just focusing on the x, is a superposition of plus and minus waves. Waves with plus positive and negative momentum. So how do we get that? Well, we can write that as phi is equal to e to the I kx, phi y, phi z, plus e to the minus I kx, also for x, phi y, phi z with the same phi y and phi z. So these are actually in there. Yeah.
I still see like why any of the epsilons can't have a negative sign, you have like an exponential, like a real exponential.
Awesome.
Of your products.
Okay, so if we had a negative epsilon, is that wave function going to be normalizable?
Can you just use the minus term?
In which direction?
Oh,
Right. So if it's converging in this direction, it's got to be growing in this direction, and that's not going to be normalizable. And so as usual with the plane wave, we can work with, it's up here, we switch around. As usual with the plane wave, we can pick the oscillating solutions. They're also not normalizable to 1, but they're delta function normalizable. So that's what we found here. It's exactly the same thing as in 1D. Yeah.
So does this mean that a superposition of plane waves with wave vector equal magnitude will also be an eigenfunction of the same energy?
Absolutely. Awesome. Great observation. So the observation is this. Suppose I take K, I'll call it K1. So this is a vector, oops, that's a 1, K1, such that K1 squared times h bar squared over 2m is equal to E1, or is equal to E. Now, there are many vectors K which have the same magnitude but not the same direction. So we can also make this equal to h bar squared, K2 squared, vector squared, over 2m, where K2 is not equal to K1 as a vector, although they share the same magnitude. Okay? So that's interesting. So that looks a lot like before. In 1D, we saw that if we have K or minus K, these have the same energy. Now, if we have any k, k1, or so this is 1D, in 3D, if we have k1 and k2 with the same magnitude and the same energy, they're degenerate. That's interesting. Why? Why do we have this gigantic degeneracy of the energy eigenfunctions for the free particle in 3 dimensions? Yeah. Awesome. So this is clearly true that there are an infinite number of momenta with the same magnitude. So there are many, but why? Why do they have the same energy? Couldn't they have different energy? Couldn't this one have a different energy? Excellent. It's symmetric. The system is invariant under rotation. Who are you to say this is the x direction? I call it y. Right? So the system is, in fact, it has a symmetry. The symmetry is rotations. And when we have a symmetry, that means there's an operator, a unitary operator, which affects that rotation. Right? The rotation operator. It's the operator that takes the vector and rotates it in some particular way. We have a unitary operator that's a symmetry that means it commutes with the energy eigenfunction, or the energy operator. But if it commutes with the energy operator, we can get degeneracies. We can get states that are different states mapped to each other under our unitary operator, under our rotation. We get states that are different states, manifestly, but which have the same energy, which are shared energy eigenvalues. Cool? And this is a really lovely example, both in 1D and 3D, that when you have a symmetry, you get degeneracies. And when you have a degeneracy, you should be very suspicious that there's a symmetry hanging around, lurking around, ensuring it. Okay? And this is an important general lesson, because way beyond the specifics of the free particle. Yeah? Yeah, it occurs in systems with bound states and systems with non-bound states. So here, we're talking about a free particle, certainly not bound. And so, for bound states, we'll also see that there will be a degeneracy associated with symmetry. And your question is a really, really good one, because what we found in, let me rephrase the question, look, in 1D, when we had bound states, there was no degeneracy. Didn't matter what you did this, when you had bound state for non-degenerate. In 3D, we see that when you have a free particle, you get degeneracy. In fact, you get a heck of a lot more degeneracy. You get a sphere's worth, although actually that's a sphere in 0 dimension, right? It's a 0-dimensional sphere, 2 points. So you get a sphere's worth of degenerate states for the free particle. What about for bound states? Are bound states non-degenerate still? Fantastic question. Let's find out. So let's do the harmonic oscillator. Let's do the 3D harmonic oscillator to check. Okay. So the 3D harmonic oscillator potential is h bar squared, and let's pick, for fun, the rotationally symmetric 3D harmonic oscillator, m omega squared upon 2 x squared plus y squared plus z squared. This could also be written m omega squared upon 2 r squared. Yeah. So I could write it in spherical coordinates or in Cartesian coordinates. This is really vector notation. Doesn't matter. It's the same thing. 3D harmonic oscillator. So what do you immediately deduce about the form of the energy eigenfunctions? Well, we have that E phi E is equal to p squared over 2 minus h bar squared over 2m. So here's the energy eigenvalue equation times px squared plus py squared. Oh, sorry, dx squared plus dy squared plus dz squared plus m omega squared upon 2 times x squared plus y squared plus z squared phi e. But I can put this together in a nice way. This is minus h bar squared upon 2m dx squared plus m omega squared upon 2 x squared plus ditto for y plus ditto for z phi e. Yeah? Everybody agree? So this is a differential operator that only involves x, doesn't involve y or z. Ditto y, but no x or z, and ditto z, but no x or y. Aha! This is separable, just as before. So now we have a nice separable system where I want to solve the equations 3 times, once for x, y, and z, and now I'm just going to write it for x, y, and z. Epsilon sub x, phi x, is equal to minus h bar squared over 2m dx squared plus m omega squared upon 2 x squared phi sub x, and ditto for x, y, and z, and then phi e is going to be equal to phi x of x, phi y of y, and phi z of z. Okay, where e is equal to epsilon x plus epsilon y plus epsilon z. Note that I've used a slightly different definition of epsilon here as before. Here it's explicitly the energy eigenvalue. So what this is telling me is, look, we know what this equation is. This equation is the same equation we ran into in the 1D harmonic oscillator. It's exactly the 1D harmonic oscillator problem. So the solution to the 3D harmonic oscillator problem can be written for energy eigenfunctions, can be constructed by taking a harmonic oscillator in the x direction, and we know what those are. There's a tower of them, there's a ladder of them created by the raising operator and lowered by the lowering operator. And similarly for y and similarly for z. So I'm going to write this slightly differently in the same place as phi sub e is equal to phi sub nx of x, the state with energy E sub nx, phi sub ny of y, phi sub nz of z, where these are all the single dimension, one-dimensional harmonic oscillator eigenfunctions, and E is equal to Ex, E sub nx, plus E sub ny, plus E sub nz. Okay. So let's look at the consequences of this. So first off, does anyone have any questions? I went through that kind of quick. Any questions up there? Okay, if you're not comfortable with separable equations, you need to become super comfortable with separable equations. It's an important technique. We're going to use it a lot. So the upshot is that if I write, in fact, I'm going to write that in a slightly different notation. If I write phi e is equal to phi n of x, where it's the and phi L of y, yeah, fine, and phi m of z. Actually, that's a stupid order. Let's try that again. L, M, N, that is the alphabetical ordering. Okay, with the energy is now equal to, we know the energy is of a state with of a harmonic oscillator with excitation number L. It's h bar omega, the overall omega, times L plus 1/2. But from this guy, it's got excitation number m, so energy of that is h bar omega m plus 1/2 plus m, and so now that's plus 1. And for this guy, similarly, h bar omega n plus n, and now plus 1/2 again, plus 3/2. So this is the general solution of, or sorry, this is a basis of solutions of the energy eigenfunction equation. These are the solutions, the energy eigenfunctions. For the 3D harmonic oscillator. And now here's the question. The question that was asked is, look, there are no degeneracies in bound states in 1D. Here we have manifestly a 3D bound state system. Are there degeneracies? Yeah, obviously, right? So for example, if I call L1 this 0 and this 0, or if I call this 0, 1, 0, or 0, 0, 1, those all have the same energy. They have the energy h bar omega naught times 1 plus 3/2 or 5/2. So let's look at this in a little more detail. Let's write a list of the degeneracies as a function of the energy. So at energy, what's the ground state energy for the 3D harmonic oscillator? 3/2 h bar omega, it's 3 times the ground state energy for the single 1D harmonic oscillator. So 3/2 h bar omega. Yeah. Good. The way we arrived at this was we found that the energy, so the energy operator acting on the 3D wave function is what I get by taking the energy operator in 1D and acting on the wave function, and the energy operator in Y acting on the wave function, the energy operator in Z acting on the wave function, where the energy operator for each of those is the 1D harmonic oscillator with the same frequency. Okay? And then I separated it. I said, look, let the wave function, the 3D wave function, since I know this is separable, and each separated part of the wave function satisfies the 1D harmonic oscillator equation, I know what the eigenfunctions of the 1D harmonic oscillator energy eigenvalue problem are. They're the phi n's. And so I can just take my 3D wave function. I can say the 3D wave function is going to be the separated form, the product of a 1D wave function in x, a 1D wave function in y, and a 1D wave function in z. Cool? So now let's look back at let's think about what happens when I take the energy operator and I act on that guy. When I take the 3D energy operator, which is the sum of the 3 1D energy operators, harmonic oscillator energy operators, when I take them and act on this guy, the first one, which only knows about the x direction, sees the y and z parts as constants, And it hits a phi x, and what does it give us back? E on phi x is just h bar omega n plus 1/2. Ditto for this guy. And then the energy operator in the 3D is the sum of the three 1D energy operators. So that tells us the energy is the sum of the three energies. Is that cool? Okay, good. Other questions? Yeah. Ask me that after class. Okay. So 3/2. So let's look at the degeneracies as a function of the energy. So at the lowest possible energy, 3/2 omega, what states can I possibly have? Well, I'm going to label the states by the three numbers L, M, and N. So this is just the ground state 0, 0, 0. So is that degenerate? No, because there's just the one state. What about at the next level? What's the next allowed energy? 5/2. Okay, 5/2. So at 5/2, what states do we have? Well, we have 1, 0, 0. But we also have 0, 1, 0, 0, 0, 1. Aha! This is looking good. What does this correspond to physically? This says you have excitation. So in theory, you've got a node in the x direction. But you have your Gaussian in the y and the z directions. And this one says your Gaussian in the x direction, you have a node in the y direction as a function of y because it's phi 1 of y, and your Gaussian in the z directions. This one says you have one excitation in the z direction. So they sound sort of rotated from each other. That sounds promising. Okay. But in particular, what we just discovered, sort of by construction, is that there can be degeneracies among bound states in 3D. This was not possible in 1D, but it is possible in 3D, which is cool. But we actually learned more. What's the form of the degeneracy? So here it looks like they're just rotations of each other. You call this x, I call it y, someone else calls it z. These can't possibly look different as functions because they're just rotations of each other. Yeah. However, things get a little more messy when you write, well, what's the next level? What's the next energy after 5/2 h bar omega? 7/2 h bar omega, exactly. 7/2. And that's not so bad. So for that one, we get 2, 0, 0, 0, 2, 0, 0, 0, 2. But is that it? What else do we get? Yeah, 1, 1, 0, 0, 1, 1, 1, 0, 1. So first off, let's look at the number. The degeneracy number here, I'll call this d sub 0. The degeneracy of the ground state is 1. Okay. The degeneracy, and if I can write this as a table, the degeneracy of level n. So for d0 is equal to 1, d1 is equal to 3, and d2 is equal to 6. Now, it's less clear here what's going on, because is this just this going to be labeled? No. So this is weird, because we already said that the reason we expect that there might be degeneracy, is because of rotational symmetry. The system is rotationally invariant. The potential, which is the harmonic oscillator potential, doesn't care in what direction the doesn't care in what direction the radial displacement vector is pointing. It's rotational symmetry. When we have symmetry on general grounds, when we have a symmetry, we expect to have degeneracies. But this is kind of weird because these don't seem to be similar rotations of each other, and yet they're degenerate. So what's up with that? Question? Yeah. Yeah, sure. Okay, good. So let me just explain what this notation means again. So by 1, 0, 0, what it means is that the number L is equal to 1, the number n is equal to 0, and n is equal to 0. That means that the wave function phi 3D is equal to phi 1 of x, phi 0 of y, phi 0 of z. Okay, but what's phi 0 of z? It's a Gaussian in the z direction. Phi 0 of y, that's the ground state in the y direction. It's a Gaussian in the y direction. Phi 1 of x, that's not the ground state, that's excited state. And if it goes to being a Gaussian, it goes through 0. It has a node. So this wave function is not rotationally invariant. It has a node in the x direction, but no nodes in the y and z direction. Okay? And similarly for these guys. Did that answer your question? Great. Okay, so we have these degeneracies. And they beg an explanation. And if you look at the next level, it turns out that D3, and you can do this quickly in a scrap of paper, D3 is 10. Okay? And they go on. And if you keep writing this list out, I guess it goes up with the next one, 15, for 1, yeah. So this has a simple mathematical structure, and you can very quickly convince yourself of the form of this degeneracy. Dn is n plus 1 over 2. So let's just make sure that works. 1 plus 1 over 2. Sorry, I should really call this 1. N plus 1, n plus 2. If I count from 0. So for 0, it's going to give us 1 times 2 over 2. That's 1. That works. So for 1, it's just 2 times 3 over 2, which is 3, and so on. Okay. So where did this come from? This is something we're going to have. I want to answer. Why that degeneracy? That seems important. Why is it that number? Why do we have that much degeneracy? But the thing I really want to emphasize at this point is that there's an absolutely essential, deep connection between symmetry and degeneracy. If we didn't have symmetry, we wouldn't have degeneracy. We can see that very easily here. Imagine that this potential was not exactly symmetric. Imagine we made it slightly different by adding a little bit of extra frequency to z direction. Make the z frequency slightly different. Plus m omega tilde squared upon 2 z squared, where omega tilde is not equal to omega naught. Okay, the system is still separable, but this guy has frequency omega naught. The x part has omega naught, this has omega naught, but this has omega tilde. Okay? And so exactly the same argument is going to go through, but the energy now is going to have a different form. The energy is going to have h bar omega L, h bar omega naught times L plus M plus 1. But from the z part, it's going to have plus h bar omega tilde times n plus 1/2. Okay. And now these degeneracies are going to be broken because this state will not have the same energy as this here. Ever see that? When you have symmetry, you get degeneracy. When you don't have a symmetry, you do not get degeneracy. This connection is extremely important because it'll... allows you to do two things. It allows you to first not solve things you don't need to solve for. If you know there's a symmetry, solve it once and then compute the degeneracy and you're done. On the other hand, if you have a system and you see, just manifestly, you measure the energies, and you measure that the energies are degenerate, you know there's a symmetry protecting those degeneracies. You actually can't be 100% confident because it didn't prove that these are related to each other. But you should be highly suspicious. And in fact, this is an incredibly powerful tool in building models of physical systems. If you see a degeneracy or an approximate degeneracy, you can exploit that to learn things about the underlying system. Yeah. Yes. Exactly. So it's possible. It's possible for these omegas to be it's possible for these omegas to be specially tuned so that rational combinations of them give you a degeneracy. But it's extraordinarily unlikely for that to happen accidentally because they have to be rationally related to each other, and the rationals are set to measure 0 in the reals. Right? So if you just randomly pick some frequencies, they'll be totally commensurate. You'll never get a degeneracy. So it is possible to have an accidental degeneracy. Whoops. Just pure coincidence. But it's extraordinarily unlikely. And as we'll see when we get to perturbation theory, it's more than unlikely. It's almost impossible. So it's very rare that you get accidental degeneracy. It happens, but it's not. It's rare. Other questions? Okay. Nothing? Okay, so here we're now going to launch into, so this leads us into a very simple question. At the end of the day, the degeneracies that we see for the 3D free particle, which is a whole sphere's worth of degeneracy, and the degeneracy we see for the 3D harmonic oscillator, the bound states, which is discrete, but with more and more degeneracy, the higher and higher energy you go. Those we're blaming at the moment on a symmetry, on rotational symmetry, rotational invariance. So it seems wise to study rotations, to study rotational invariance and rotational transformations in the first place. In the first part of the course, in 1D quantum mechanics, we got an awful lot of juice out of studying translations, and the generator of translations was momentum. So we're going to do the same thing now. We're going to study rotations and the generators of rotations, which are the angular momentum. So that's going to occupy the rest of today and Thursday. Yeah.
We explain a factor of 3 in your degeneracy, right? But what's the symmetry that explains the way this goes? Because it's like very clearly there's one up to a factor of 3, and there's 2 up to a factor of 3, and then there's even more. Multiple 3. Right.
Actually, so here's a very tempting intuition. Very tempting intuition is going to say the following. Look, rotational invariance, well, there's X, there's Y, and there's Z. It's going to explain the rotations amongst those 3. So, that can only possibly give a factor of 3. But it's important to keep in mind that that's not correct intuition. It's tempting intuition, but it's not correct. And the easy way to see that it's not correct is that for the free particle, there is a continuum, a whole sphere's worth of degenerate states and the energy. And all of those are related to each other by simple rotation of the K vector, of the wave vector. Right? So the rotational symmetry is giving us a lot more than a factor of 3. And in fact, as we'll see, it's going to explain exactly the n plus 1 and plus 2 over 2. Okay, so with that motivation, let's start talking about angular momentum. So I found this topic to be not obviously the most powerful or interesting thing in the world when I first studied it, and my professor was like, no, this is the deepest thing. And recently I had a fun conversation with one of my colleagues, Frank Wilczek, who said, in intro quantum mechanics, the single most interesting thing is angular momentum and the addition of angular momentum. And something has happened to me in the intervening 20 years that I totally agree with. So I will attempt to convey to you with the awesomeness of this, but you have to buy in a little. So work with me in the math at the beginning of this, and it has a great payoff. Okay, so the question is, what is the operator? So here, let's start. So we're going to talk about angular momentum now. And I want to start with the following question. In the same sense as we started out by asking what represents position in momentum, linear momentum, in quantum mechanics, what operator, by our first, our second or third postulate, I don't even remember the order now, what operator represents angular momentum in quantum mechanics? Okay. And let's start by remembering what angular momentum is in classical mechanics. So L, in classical mechanics, is R cross B. In classical mechanics. So let's just try this. Let's construct that the operator, this is not the most beautiful way of deriving this, but a natural guess for in quantum mechanics. What's the operator we want? Well, we want a vector's worth of operators. Right? Angular momentum is a vector. There's a vector of operators, 3 operators, and I'm going to write these as R vector, the operators, x, y, z, cross P, the vector of momentum operators. So at this point, you should really worry because do R and P commute?
No.
Not so much, right? However, the situation is better than it first appears. Let's write this out in terms of components. So this is in components. And I'm going to work for the moment in Cartesian coordinates. So Lx is equal to, you all took mechanics. Lx is equal to, thank you, ypz minus zqy. Good. And that's the curl, the x component of the curl. Okay. And similarly, the x component, so this is, the way to remember this is that it's cyclic. X, y, z, y, zx. So z, py. I'm sorry, z, px, px, minus x, pz. And now we have z, xpy minus ypx. Okay. And now, so we were worried here about maybe the ordering problem. Is there an ordering problem here? Does it matter if I write ypz or pzy? No, because they commute with each other. Pz is the momentum for the z coordinate, not the y coordinate. They commute with each other. So there's no ambiguity. It's perfectly well defined. So we're just going to take this to be the definition of the components of the angular momentum operator Lx, Ly, and Lz. And just for fun, I want to write this out. So this is because we know that Px, Py, and Pz can be expressed in terms of derivatives or differential operators. We can write the same operator in Cartesian coordinates in the following way. So clearly we can write this as y dx I upon h bar, or sorry, h bar upon I, and z h bar upon I dy. So we can write that in Cartesian coordinates as a differential operator. But we can also write this in spherical coordinates. I'm just going to take a quick side note just to write down what it is. If we did this in spherical coordinates, it's particularly convenient to write, let me just write Lz for the moment. This is equal to minus I h bar, derivative with respect to phi, where the coordinates, the way I'm going to name coordinates and spherical coordinates in this class is theta is going to be the angle down from the vertical axis from the z-axis, and phi is going to be the angle of the period 2 pi that goes around the equator. Okay, just to give you a name. This is typically what physicists call them. This is typically not what mathematicians call them. This leads to enormous confusion. I apologize for my field. So here it is. I can also construct the operator associated with the square of the momentum. And why would we care about the square of the momentum? Well, that's what shows up in the Hamiltonian. That's what shows up in the energy. So I can construct the operator for the square of the momentum and write it, and it takes a surprisingly simple form. When I say surprisingly simple, you might disagree with me, but if you actually do the derivation of this, it's much worse in between. Over sine theta, theta, sine theta, theta, plus 1 over sine squared theta, d phi. A couple quick things. What are the dimensions of angular momentum? Length and momentum. What else has units of angular momentum? Solid. H bar, dimensionless. Angular momentum squared, angular momentum squared. Okay, great. So that's going to be very convenient. H bars are just going to float around willy-nilly. Okay, so suppose I ask you the following question. Suppose I ask you the following questions. I say, look, here are the operators of angular momentum. This Lz, we could have written down as
Just going to write this as that.
expression for Lx and the y, and L squared. What are the eigenfunctions of these operators? Suppose I ask you this question. You all know how to answer this question. You take these operators. So for example, if I ask you what are the eigenfunctions of Lz, well, that's not so bad, right? The eigenfunction of Lz is something where Lz on phi, so I'll call it little m, is equal to minus I h bar d theta phi sub m. But I want the eigenvalue, so I'll call this h bar times some number. Let's call it m. Okay, because Lz is an angular momentum carries the units of h bar, and h bar times some number is dimensional, so we'll call it m. And we all know the solution to this equation. The derivative is equal to a constant times. You can lose the h bars. We get minus I, so we pick up an I. So therefore, phi sub m is equal to some constant times e to the I m phi. What can we say about m? Well, here's an important thing. Oh, shoot. I'm using phi in so many different ways here. Let's call this not phi, because it's going to confuse the heck out of us. Let's call it y. Okay, so we'll call it y sub m. Why not? It's not my joke. This goes back to a bunch of, yeah, well, it's good to be back. So phi is the variable, y is the eigenfunction of Lz. And that's great. But what can you say about m? Well, phi is the variable around the equator periodic with period 2 pi. And our wave function had better be single value. So what does that tell you about m? Well, under phi goes to phi plus 2 pi, this shifts by I m 2 pi. And that's only 1 to make a single value if n is an integer. So n has to be an integer. Okay. Now, we did that for Lz. We found the eigenfunction of Lz. What about finding the eigenfunction of L squared? Okay, exactly the same thing. We're going to solve the eigenvalue equation, but it's going to be horrible. horrible to find these functions, right? Because look at this, 1 over sine squared d phi, and then 1 over sine d theta sine d theta. It's not going to be a fun thing to do. So we could just reinforce this, but let's not. Let's all agree that that's probably a bad idea. Let's find a better way to construct the eigenfunctions of the angular momentum operators. So let's do it. So we ran into a situation like this before when we dealt with the harmonic oscillator. There was a differential equation that we wanted to solve. And okay, this one isn't nearly as bad, not nearly as bad as that would have been, but still it's more useful to work with operator methods. So let's take a hint from that and work with operator methods.
Let me just write that down. Try here.
So now we need to study the operators of angular momentum. So let's study them in a little more detail. So something you're going to show in your problem set is the following. The commutator of Lx with Ly takes a really simple form. This is equal to IH bar. Well, let's just do this out. Let's do this commutator. We're okay. So Lx with Ly. This is equal to the commutator of ypz minus zpy with y zpx minus fpz. So let's look at these term by term. So the first one is ypz zpx. Ypz zpx. Oops, that's bx. Oh, sorry, zpy. zpx. This term. X. Good. That's the first commutator. The second commutator is going to be ypz and xpz minus ypz xpz. Okay. And then these commutators, the next two are going to be zpy, zpy with zpx. And finally zpy, and that's minus and plus, zpy and xpz. Okay, so let's look at these. These look kind of scary at first, but in this one, notice the following. This is x, pz, zpx minus zpx, ypz. But what can you say about y with all these other operators? Y can use with all of them. So in each term, I can just pull y all the way out to one side. Yeah? So I just pull out this y. So for the first term, I'm going to write this as y, commutator pz with z px. Okay, let me just do that explicitly. There's no reason not to. So this is y pz z px minus z px y pz. And I can pull the y out front because this can use with px and with z. So I can make this y times pz z px minus z px pz. But now note that I can do exactly the same thing with the px. Px can use with z, px can use with pz, and I can use with y. So I can pull the px from each term out. Px, y. And I lose the px. I lose the px. But now this is looking good. This is px times y, and pz minus z pz. Pzz minus z pz. This is also known as, pxy times commutator of pz with z. And what's this equal to? Let's get our signs right. This is px with y times, okay, we all agree that this is going to have an h bar in it. It's for units. There's going to be an I. And is it a plus or minus? Minus. Okay, good. So we get minus I h bar x py. Okay, so this term is going to give us minus I h bar py x px times y. And let's look at this term. Okay, this is y and And y commutes with pz, x, and pz, right? So I can just pull out the y, and x commutes with everything, so I can pull out the x. And I'm left with the commutator pz with pz. What's commutator pz with pz? 0. This term gives me 0. Similarly here, py commutes with everything, z, z, px. Px commutes with everything, z, z, py. So I can pull the px and py, and then z commutator p, and what's that? 0. So this gives me 0. And now this term, z, py, x, pz, the only two things that don't commute with each other are the z and the pz. The px and the py and the x are pull out. So I get a term x, py, and the commutator z with pz. And what is that going to give me? Pyx I h bar. Aha! Look at what we got. This is equal to I h bar times Pyx, or sorry, fpy minus y pz. Oh, sorry, Px. And what is this equal to? Yeah, I h bar LZ. Okay. And more generally, as you'll show on the problem set, you get the following commuters. Once you've done this once, you can do the rest very easily. Lx Ly is, so Lx with Ly is I h bar LZ. And then by cyclic, and then the rest we got from cyclic rotations, Ly with Lz is I h bar Lx, and Lz with Lx is I h bar Ly. And now here's a fancier one. This is less obvious, but exactly the same machinations will give you this result. You'll do this again on the problem set. If I take L squared, okay, and L squared here is going to be L squared. I just need Lx squared plus Ly squared plus Lz squared. This is the norm squared of the vector of the operator form. L squared with Lz, or sorry, with Lx. Yeah, fine. Lx is equal to 0. So Lx commutes with the magnitude L squared. Similarly, L squared, now just by rotational invariance, if Lx commutes with it, Ly and Lz that also commute with it. Because for you to say what's Lx, and L squared with Lz must be equal to 0. Yeah? We're cool with that? And the thing is, we've just, I'm going to put big flags around this, we've just learned a tremendous amount of the eigenfunctions of the angular momentum operators. Why? So what have we just learned about the eigenfunctions of the angular momentum operators Lx, Ly, Lz, and L squared? Anyone? We just learned something totally awesome about them.
Like a ladder that rotates?
Anyone? So, can you find simultaneous eigenfunctions of Lx and Ly?
No.
Not so much. They don't commute to 0. What about Ly and Lz? Nope. Lz, Lx? Nope. So you cannot find simultaneous eigenfunctions of Lx and Ly. What about Lx and L squared? Yes. So we can find simultaneous eigenfunctions of L squared and Lx. Okay. What about, can we find simultaneous eigenfunctions of L squared and Ly? Yep, exactly. What about L squared, Ly, and Lz? Nope. No such luck. Right? And this leads us to the following idea. The idea is a complete set of commuting observables. And here's what this idea is meant to contain. You can always write down a lot of operators. So let me step back and ask a classical question. Classically, suppose I have a particle in 3 dimensions. A particle moving around in this room. Non-relativist. Familiar data 1. I have a particle moving around in this room. How much data must I specify to specify the configuration of the system? Well, I have to tell you where the particle is, and I have to tell you where the momentum is. Right? So I have to tell you the 3 coordinates and the 3 momentum. If I give you 5 numbers, that's not enough. Right? I need to give you 6 bits of data. On the other hand, if I give you 7 numbers, I give you x, y, z, px, py, pz, and e, that's overcomplete. Right? That was unnecessary. Okay. So in classical mechanics, you can ask what data must you specify to completely specify the state of the system? And that's usually pretty easy. You specify the number of coordinates and the number of dimension. In quantum mechanics, we ask a slightly different question. We ask, in order to specify the state of the system, we say if we want to specify which state it is. You can specify that by saying which superposition in a particular basis. So you pick a basis and you specify which particular superposition. What are the eigenvalues of the operators you diagonalize in that basis? So another way to phrase this is for a 1D problem. Say we have just a simple 1D problem. We have x and we have p. What is a complete set of commuting operators? Well, you have to have enough operators so that the eigenvalue specifies the state. So x would be, is that enough? So if I take the operator x and I say, look, my system is in a state with an eigenvalue of x, not of x, does that specify the state of the system? It tells you the particle is in a delta function state right here. Right? Does that specify the state? Fantastic, it does. Now, what if I tell you instead, oh, it's in a definite state, a state of definite p? Does that specify the state? Absolutely. Can I say it's in a state with definite x and definite p? No, these don't commute. So a complete set of commuting observables in this case would be either x or p, but not both. Yeah? Now, if we're in 3 dimensions, is x a complete set of commuting observables? No, because it's not enough to tell me that it's x. It doesn't tell me what state it is because it could have y dependence or z dependence. So in 3D, we'd pick, for example, x and y and z. Or px and py and pz. We can also pick z and px and y. Right? Are these complete? If I tell you I have definite position in z, definite position in y, and definite momentum in x, Does that completely specify the state? Yeah, totally unambiguously. EVIKX, delta y, delta z. Totally fixes my function. Completely specifies it. If I only picked two of these, it would not have been complete. Right? So it would have told me, for example, I have EVIKX, delta y, but it doesn't tell me how it depends on z. And if I added another operator, for example, py, this is no longer commuted. These two operators don't commute. So a complete set of commuting observables can be thought of as the most operators you can write down that all commute with each other, and the minimum number that whose eigenvalues completely specify the state of the system. Cool? So, with all that said, what is the complete set of commuting observables for the angular momentum system? Well, it can be any two of Lx, Ly, and Lt. So let's just pick one. I'll call it Lz. I could have called it Lx. It doesn't matter. It's up to you what axis is what. I'll just call it Lz conventionally. And then L squared also commutes, because L squared commutes with Lx, it commutes with Ly and with Lt. So this actually forms a complete set of commuting observables for the angular momentum system. Complete set of commuting observables for angular momentum. So this idea will come more in the future. And here's going to be the key. Here's going to be the key juice. So we'd like to use the following fact. We want to construct the eigenfunctions of our complete set of. Oh yeah, question.
How you got it, the L squared and LXT?
Yeah, I got it by knowing what you're going to write on your solution set. So this is on your problem set. So the way it goes, so there are fancy ways of doing it. The direct way of doing it, how you construct these commutators, is you know what the operators are, you know what L squared is, and you know that L squared is L squared plus Ly squared plus Lt squared. It's built in that fashion of X and Py. And then I literally just put in the definition of Lx, Ly, and Lt into that expression for L squared, and compute the commutator with Lx, again, using the definition in terms of Py and Z. And then you just chunk through the commutators. Yeah, it just works out. So it's not obvious from the way I just phrased it that it works out like that. Later on, you'll probably develop some intuition that it should be obvious. But for the moment, I'm just going to call it a brute force computation. Okay, and that's how you're going to do it on your problem set. So let me tell you where we're going next. So the question I really want to deal with is, what are the eigenfunctions? This is where we're leading off. What are the eigenfunctions of our complete set of commuting observables, L squared and Lz? Okay, what are these guys? And we know that we can solve them by solving the differential equations using those operators. That would be horrible. We'd like to do something a little smarter. We'd like to use the commutation relations in the algebra. And here, a really beautiful thing is going to happen. When you look at these commutation relations, one thing they're telling us is that we can't simultaneously have eigenfunctions of Lx and Ly. However, the way that Lx and Ly can get together is to form Lz. That gives us some information. That gives us some magic, some power. And in particular, much like that moment in the harmonic oscillator, I said, well, look, we can write down these operators A. Well, look, we can write down these operators, which I'm going to call L plus and L minus. L plus is going to be equal to Lx plus I Ly. And L minus is going to be equal to Lx minus I Ly. Now, Lx and Ly, those are observables. What can you say about them as operators? What kind of operators are they instead of observables? Hermitian, exactly. So what's the Hermitian adjoint of Hermitian plus I Hermitian? Hermitian minus I Hermitian. Okay, good. So L minus is the adjoint of L plus. Okay. So this is just going to be a definition. Let's take these to be the definitions of these things. If we take a commutator, something totally lovely happens. I'm not going to write all the commutations. I'm just going to write a couple. The first is, if I take L squared and I commute with L plus, well, L plus is Lx plus Ly, and we already know that L squared commutes with Lx and it commutes with Ly. So L squared commutes with L plus. And similarly for L minus, it commutes with each term. Question? Oh, sorry, Lx. Shoot, that was an X. It just didn't look like it. Lx minus Ly. So it commutes with both L plus and L minus. But here's the real beauty of it. Lz with L plus is equal to, well, let's just do dimensional analysis. L plus is Lx plus I Ly. We know that Lz with Lx is something like Ly, and Lz with Ly is something like Lx, with factors of i's and h bars. And when you work out the commutator, which should only take a second, get I h bar L plus. And similarly, when we construct Lz and L minus, we get minus h bar L minus. Are L plus and L minus Hermitian? No, they're each other's adjoints. Lz is Hermitian. And look at this commutation relation. What does that tell you? From the first observation, if we have an energy, or if we have an operator E and an operator A that commute in this fashion, then this tells you that the eigenfunctions of this operator are staggered in the ladder space by h bar. The eigenvalues of Lz come in a ladder spaced by h bar. We can raise with L plus, and we can lower with L minus, just like in the harmonic oscillator problem. Okay? And we'll explain the rest of we'll deduce the rest of the structure of the angular momentum operator eigenfunctions next time using this commutation relation. See you next time.
Okay, I'm a little bit over there, but I think we've gotten done 3 classes. Let's look at some of the issues here. I don't feel like there was anything too difficult in this lecture about 3D harmonic oscillator. I feel like I understood most of the stuff that was going on here. I think I'm going to have some difficulties in the problem sets, particularly because A lot of my vector calculus is not quite as strong as I'd like it to be. Let me just get here. Particularly because my vector calculus is well, it's rusty like everything else is, but I haven't done any practice on it yet because we were working the one-dimensional case. Also, I think, once you start working in cylindrical and spherical coordinates, you're going to have a lot of trigonometry. You're going to have to be very careful about how you carry things. So that might require some extra practice. I don't think those are necessarily conceptual weaknesses, but definitely at the level of calculating, there's going to be challenges there. So I think overall, I mean, in the previous lecture, so lecture 14, there was some stuff involving, when we're talking about the scattering here, there was some stuff involving this here, which was about 21 minutes that, I mean, I understood it. I understood kind of qualitatively the result here, but in terms of what was happening with the exact calculation, this whole idea of stationary phase, again, this could be 803 stuff. I'm blaming a lot on 803. It could also just be from here, and I don't understand it. So I don't want to say that necessarily this is 803 stuff, but I think it was just because this is kind of wave packet idea moving over some of these ideas like stationary phase and how it's working out, didn't completely understand. But it looks like we moved on from that. It looks like we just put that aside. So I don't think that there's going to be a dependency in the future lectures on having understood that. So I'll probably do what I did last time, which is revisit it when that becomes an issue or when understanding that derivation becomes more important. Obviously, there's going to be a lot of stuff to learn, a lot of stuff to practice. I'm not only going to have to finish all these lectures and make sure I understand the conceptual points behind this very well, but there's going to be a lot of stuff, not only just the problem sets, but I think if the next 5 problem sets are anything like the first 5 problem sets, then it's going to be a lot of extra practice I'm probably going to need. So I'm going to probably be using the problem sets in here. Maybe I can try to find some extra problem sets through digging around in Stellar. I didn't, prior to preparing for this, didn't drill up extra problem sets, although that might be something I'm going to need. And not to mention that it's also maybe going to be the case that I'm going to want to go back to some problem sets of some basic calculus, multivariable calculus, these kind of things, just so that I feel more comfortable. Very often you don't need to do that if you can just work through the higher level problems. But if you're working through a problem, you're like, wait, I don't understand at all how they got this result. Sometimes it makes sense to just take a step back and work on that prerequisite. So hopefully everything has been okay with the live stream. I know I had a little bit of a glitch. I think I might have had it where the camera was just on me when I was doing that first class. So I apologize about that. I'm still getting used to the live streaming software and making sure that I'm sending things to live and doing that appropriately. But I think I'm going to take a break for lunch now, and then I will be back again at 2 p.m. Again, just continue with the lectures. We've been doing pretty well at the 2.5 per session. So if I get another 2.5 done, what are we at now? We have 9 left. So yeah, we're looking at maybe finishing this up by like Friday. What is that? Friday morning sometime. We'll probably be finishing up. And let's just give it a little bit of extra time because I'm probably going to need a little bit of time to sort things out. So I think we're probably on schedule for finishing all the lectures by my sort of predefined deadline. And then, of course, the real work begins of drilling through this stuff, really trying to master it by working through problem sets, building up the intuition, going through Feynman technique, doing that work. So I will take a break right now, and I will be back on at